Welcome to the Late Lab. It's lovely to have you here. Before we settle in, tell me, where in the world are you watching from tonight? Somewhere dark and quiet, under a blanket after a long day, half awake on the sofa, promising yourself you will definitely go to bed soon, while absolutely not going to bed soon. Wherever you are, I hope you're warm, comfortable, and able to let the day loosen its grip for a little while. If these slow little journeys through science help you relax, think, or drift gently towards sleep, then a like and subscribe is always deeply appreciated. It helps this quiet corner of the internet keep glowing softly in the dark. And to everyone already subscribed, thank you, truly. Your support helps more than you might imagine. Tonight, we're going to drift through 101 quantum physics facts, each one a small window into the strange rules beneath ordinary reality. Some will be simple and surprising, some will be deeply counterintuitive, and some may leave the universe looking just slightly less solid than it did a few minutes before, which is not ideal for bedtime, but very good for curiosity. The aim is to keep things calm, clear, and gentle, while moving through a world where particles behave like waves. Empty space refuses to be truly empty, and reality seems to prefer probabilities over promises. If sleep arrives somewhere around fact 37, wonderful. If curiosity keeps you awake until fact 101, then at least the night has been educational. So let's begin. What is quantum physics, and why does the smallest layer of reality seem so much stranger than the world we wake up in every day? The world around you does not usually feel mysterious in any practical sense. A table feels like a table. A beam of light moves across a wall. A warm mug cools slowly in your hands. The air in the room does not appear to be made of rules, limits, and probabilities. It simply feels like air. Everything seems continuous, familiar, and pleasantly normal, which is exactly the sort of confidence the universe allows at large scales before quietly becoming very strange underneath. Quantum physics begins with that underneath. It is the science of nature at extremely small scales, where energy, matter, light, and information stop behaving like the objects of daily life. It does not say that the everyday world is fake, or that reality is whatever anyone imagines it to be. It says something more precise, and in some ways more unsettling. Beneath the smooth surface of ordinary experience, nature appears to work through packets, boundaries, probabilities, and patterns that cannot be fully described by classical physics alone. One of the first clues came from a very ordinary question. How do hot objects glow? This sounds gentle enough, almost domestic. A piece of metal in a fire begins dark, then red, then orange, then white hot. The glow changes as the temperature rises. Classical physics could describe many things beautifully, from falling apples to orbiting planets, but when physicists tried to calculate the exact pattern of light from a perfectly absorbing and emitting object, the results went badly wrong. The equations predicted far too much energy at short wavelengths, an impossible disaster sometimes called the ultraviolet catastrophe. Reality, with excellent comic timing, refused to explode in ultraviolet light just because the mathematics said so. This was not the only problem. Atoms were also awkward. If electrons were tiny charged particles moving around a nucleus under classical rules, they should lose energy and collapse inward. Matter itself should not be stable in the way it clearly is. Then light added another puzzle, because in some experiments it behaved like a wave spreading smoothly through space, while in others it seemed to arrive in separate little pieces. Quantum physics grew out of these cracks, not from a desire to make science sound mysterious, but from the fact that nature kept giving answers classical physics could not honestly explain. The word quantum means a discrete amount, a little packet, a step rather than a smooth slide. In everyday life, many things seem divisible without limit. Pour water from a jug and it flows in a continuous stream. Turn a dimmer switch and the light appears to brighten gradually. Walk across a room and the distance seems to pass smoothly beneath your feet. But at the quantum level, certain properties do not change in just any amount whatsoever. Energy can be exchanged in specific units. Electrons in atoms occupy allowed energy levels. Light can be absorbed and emitted as photons, each carrying a particular amount of energy. This does not mean everything in the universe is chunky in a simple, obvious way, as if reality were made from cosmic Lego bricks. Quantum physics is subtler than that. The mathematics often involves waves, fields, and probabilities that spread continuously, but the results of interactions and measurements often appear in definite units. A detector clicks. An atom absorbs one photon. An electron changes from one allowed state to another. The smoothness has not vanished completely, but it is no longer the whole story. Nature behaves as though it has rules about how finely certain things can be divided, and those rules become impossible to ignore when the scale becomes small enough. Max Planck introduced the quantum idea in 1900 while studying black-body radiation. A black body is an idealized object that absorbs all incoming radiation and emits light according to its temperature. It sounds a little dramatic, but it is not a sinister object in a cloak. It is a very useful physical model. Planck was trying to match the observed spectrum of glowing hot objects, and the only way he could make the mathematics fit was to assume that energy was emitted or absorbed in small discrete units. He did not begin by announcing a grand revolution. He was, in a sense, trying to repair a stubborn calculation. That is one of the quietly charming things about the birth of quantum theory. It did not arrive as a polished philosophy of reality. It arrived as a reluctant solution to a technical problem. Planck found that the energy of radiation was linked to frequency through a tiny constant, now called Planck's constant. That constant sets the scale of quantum effects. It is extremely small, which is why quantum behavior usually stays hidden in ordinary life. But small does not mean unimportant. A tiny hinge can hold a very large door, and Planck's constant became one of the hinges on which modern physics turned. Quantum physics does not replace everyday physics in the situations where everyday physics already works. A thrown ball still follows a path that can be described very well without solving the full quantum behavior of every atom inside it. A bridge does not need quantum mechanics to explain why it stands under normal loads. The moon does not need to be treated as a blurry probability cloud when calculating its orbit around Earth. Classical physics remains incredibly useful because large objects are made from vast numbers of quantum parts whose delicate possibilities usually average into stable, predictable behavior. But quantum physics explains why those larger things can exist in the first place. It explains why atoms have structure, why elements have different chemical properties, why solids are solid, why metals conduct, why semiconductors can be tuned into electronics, and why light interacts with matter in the precise ways it does. It sits underneath the ordinary world like a hidden grammar. Most of the time, the listener does not need to think about grammar to enjoy a sentence, but the structure is still there, quietly holding the meaning together. This is why quantum physics can feel both distant and intimate. It deals with scales far smaller than anything the eye can see, yet it helps explain the glow of a lamp, the colour of a leaf, the workings of a phone, the stability of a molecule, and the light from a star. It is not a separate magical realm beneath the real world. It is part of the real world, revealed when instruments and mathematics become sensitive enough to notice what ordinary senses cannot. So the first strange fact to carry gently forward is that reality is not as smooth underneath as it appears from the surface. The familiar world is not an illusion, but it is an emergent calm, built from deeper rules that are more constrained, more probabilistic, and more delicate than everyday intuition expects. Quantum physics is strange not because it is loose, mystical, or made from clever wordplay, but because it is precise in a way that does not resemble common sense. Beneath the steady table, the quiet wall, the warm light, and the sleeping room, nature keeps its smallest accounts in packets, possibilities, and patterns. The surface feels continuous. The depths are more finely written. Light is one of the most familiar things in the world and one of the least obedient. It fills a room, warms the skin, paints colour onto objects, and travels through space so reliably that stars can send their stories across unimaginable distances. In ordinary life, light feels simple because it is always there, doing its work quietly. It arrives through windows, glows from screens, spills from lamps, and generally behaves itself, which is kind of it, considering what it is hiding. At smaller scales, light becomes one of the first great hints that nature does not fit neatly into the categories humans like to build. It can behave like a wave, spreading and overlapping. It can behave like a particle, arriving in separate packets. It can act continuous in one setting and countable in another. This does not mean light is confused. Light is not hovering in the corner of the universe, unable to fill out an identity form. The confusion belongs more to the human attempt to describe it using words borrowed from everyday objects. For a long time, one of the strongest pictures of light was the wave picture. This made very good sense because light can spread, bend, and interfere. When waves overlap, they can strengthen each other or cancel each other out. The same thing happens with water ripples in a pond. If two ripples meet crest to crest, the water rises higher. If a crest meets a trough, the motion can flatten. Light can produce similar interference patterns, not with water rising and falling, but with brightness and darkness appearing in carefully arranged bands. This wave behavior is not a small detail. It explains why light passing through narrow openings can spread out, why thin films can shimmer with changing colors, and why certain experiments produce patterns that look as if different portions of light have met and interacted. The wave theory of light became powerful because it could explain things that a simple particle picture struggled with. Light did not always seem to travel like a stream of tiny pellets, flying in straight lines. Sometimes it behaved more like a spreading disturbance, able to overlap with itself and leave behind a pattern that looked almost like a signature. But then light did something awkward, which is very on brand for quantum physics. It also began to behave as if it arrived in individual packets. These packets are called photons. A photon is a quantum of electromagnetic radiation, a smallest exchangeable unit of light energy. When light is detected with sensitive enough equipment, it does not always appear as a smooth flow. It can arrive as separate clicks, one event at a time, increase the brightness, and the number of photons increases. Lower the brightness enough, and the arrival of light starts to feel less like a continuous pour and more like individual drops. That image should not be taken too literally, because photons are not tiny glowing marbles. They do not have little polished surfaces or miniature headlights. A photon is a quantum object, and its behavior is described by quantum theory rather than by the habits of ordinary objects. Still, the particle-like side of light is unavoidable. Cameras, detectors, solar cells, and the cells in the eye all depend on light interacting with matter in discrete exchanges. A faint light can be so faint that its individual arrivals matter. The wave seems to spread through space, yet the detection happens in single events. Light is generous with mystery but quite strict with evidence. One of the major turning points came from the photoelectric effect. In this effect, light shining on a metal surface can knock electrons out of the metal. Classical wave theory suggested that increasing the brightness should eventually give electrons enough energy to escape, no matter what colour the light was, as though enough weak waves could gradually build up the energy required. But experiments showed something different. If the light had too low a frequency, it could be bright and still fail to eject electrons. If the frequency was high enough, electrons could be ejected even when the light was faint. Albert Einstein explained this in 1905 by arguing that light energy came in packets. Each photon carried an amount of energy linked to its frequency. If a photon had enough energy, it could knock an electron free. If it did not, no amount of patience from that individual photon would help. It was a little like trying to pay an entry fee with the wrong coin. Bringing a sack full of coins that are each too small does not help if the gate only accepts a single coin of the required value. This explanation helped establish the photon as a serious physical idea, not just a mathematical convenience. Then there is the double-slit experiment, which has become famous because it is simple to describe and deeply strange to think about. When light passes through two narrow slits and reaches a screen, it can form an interference pattern of bright and dark bands. This makes sense if light behaves like a wave passing through both openings, spreading out and overlapping on the far side. The bright bands mark places where the waves reinforce each other. The dark bands mark places where they cancel. So far, so beautifully wave-like. The deeper strangeness appears when the light is made extremely faint, so faint that photons are sent through the experiment one at a time. Each photon is detected as a single point on the screen. At first these points can look random, but as many photons arrive, one after another, the interference pattern slowly builds up. This suggests that each photon is not simply choosing one slit in the ordinary sense and behaving like a tiny bullet. The quantum description involves a spread of possible paths, and those possibilities interfere. The individual result is particle-like. The accumulated pattern is wave-like. Nature seems to be writing in dots but composing in waves. This is why the phrase wave-particle duality can be useful, but also slightly misleading if it is taken too casually. Light is not switching costumes backstage, appearing as a wave for one scene and a particle for the next. It is not secretly one ordinary thing pretending to be another ordinary thing. Wave and particle are familiar images created from the large-scale world, and light does not come from the large-scale world. It comes from the deeper rules that produce the large-scale world. Depending on how it is measured, one aspect becomes more visible than another. The calmer way to hold the idea is this: light is a quantum object. Sometimes its behavior is best described using wave language, because it spreads, overlaps, and interferes. Sometimes its behavior is best described using particle language, because it is emitted and absorbed in discrete packets called photons. Neither image alone captures the full reality. Each one is a useful doorway into something that does not perfectly resemble water ripples or flying grains of dust. So light refuses to choose one identity only because the choices are human ones. The universe is not required to sort itself into categories that feel comfortable at breakfast. Light reveals that the deep structure of nature is more flexible, more subtle, and more mathematical than everyday intuition expects. It can cross a room like a beam, spread like a wave, arrive like a particle, and build patterns one tiny detection at a time. It is familiar enough to read by, warm enough to feel, and strange enough to remind physics that reality was never obliged to be simple. Once light has already refused to behave like only a wave or only a particle, the next strange step is to ask whether light is special. Perhaps light gets to be odd because it has no rest mass, travels at the speed of light in a vacuum, and generally behaves like the universe's most elegant rule breaker. Perhaps ordinary matter, the stuff of atoms and objects and biscuit tins, is more sensible. Matter seems heavier, more definite, more committed to being somewhere. It feels like the part of reality that should politely remain particle-like. Quantum physics naturally does not allow that comfort to last for long. Matter also has wave-like behavior. Electrons, atoms, and even larger particles can show effects that once seemed to belong only to waves. This does not mean a chair is secretly sloshing around the room like a water ripple, which would make furniture shopping considerably more difficult. It means that the deeper description of matter is not simply a collection of hard little dots moving through empty space. Matter too carries a wavelength. The idea came from Louis de Broglie, a French physicist who proposed in the 1920s that if light could behave like both a wave and a particle, then perhaps matter could as well. This was a bold and beautifully symmetrical thought. Light, once treated as a wave, had gained a particle-like side through photons, so maybe electrons, usually treated as particles, had a wave-like side waiting to be noticed. De Broglie suggested that particles were associated with wavelengths, with shorter wavelengths linked to higher momentum. At first, this may sound like a mathematical trick, almost too neat to be real, but in physics a good idea has to do more than sound elegant. It has to face experiment. If electrons truly had wave-like properties, then under the right conditions they should bend, spread, and interfere. They should not merely strike a target like tiny grains of sand. They should produce patterns that reveal an underlying wave nature. De Broglie's proposal helped open the way to modern quantum mechanics, because it suggested that wave-particle duality was not a strange habit of light alone. It was a deeper feature of nature. Electron diffraction provided the crucial confirmation. Diffraction happens when waves encounter openings, edges, or repeating structures and spread or interfere in ways that depend on their wavelength. Light diffracts, water waves diffract, sound can diffract. If electrons diffracted too, then electrons could no longer be understood as ordinary little pellets. In the late 1920s, experiments showed that beams of electrons passing through crystals produced diffraction patterns, just as waves would when scattered by the regular arrangement of atoms. That result was extraordinary. An electron has mass. It carries electric charge. It can be detected as a localized event. Yet when many electrons pass through the right kind of structure, the pattern they form reveals wave-like behavior. The crystal acts almost like a three-dimensional grating, scattering the electron wave in particular directions. The result is not a vague philosophical suggestion, but a visible experimental signature. Matter, under the right conditions, interferes. It produces patterns that cannot be explained by imagining electrons as tiny classical balls simply bouncing around. This discovery helped transform the atom from a miniature mechanical system into something much stranger and more precise. Electrons were not little planets orbiting a nucleus along neat circular paths. Their behavior had to be described by waves, probabilities, and allowed states. The wave nature of matter gave physicists a way to understand why electrons in atoms form specific patterns and why only certain energies are allowed. A stable atom began to look less like a solar system and more like a structured quantum pattern wrapped around a tiny nucleus. The reason this is not obvious in everyday life is that the wavelengths of ordinary objects are incredibly small. Everything has a de Broglie wavelength in principle, but for large, slow, human-scale objects, that wavelength is so tiny that it has no noticeable effect. A football does not diffract through a goalpost. A chair does not spread through a doorway. A slightly suspicious biscuit does not interfere with itself on the way to a cup of tea, although depending on the biscuit it may still raise questions. The larger and more massive an object is, the smaller its associated wavelength becomes at ordinary speeds. For everyday objects, the wavelength is far beyond practical detection, so classical behavior dominates. This is why the world around you looks definite and familiar. Quantum rules have not vanished, but their wave-like effects are buried under scale, complexity, and constant interaction with the environment. A dust grain, a spoon, or a sleeping cat contains an enormous number of particles, all interacting in ways that quickly wash out delicate quantum interference. Matter waves also help explain why atoms do not collapse. In a classical picture, an electron orbiting a nucleus should radiate energy and spiral inward. But in quantum mechanics, electrons are described by wave-like states around the nucleus. Only certain patterns are stable, in much the same way that a vibrating string can support certain standing waves, but not just any random shape. The electron's wave nature helps determine which arrangements are allowed. It cannot simply settle anywhere it likes. This is not a perfect visual analogy, but it is a useful one. A guitar string can vibrate in particular modes, with specific patterns of motion. In atoms, the electron's quantum state has its own allowed patterns, shaped by the attraction between the negatively charged electron and the positively charged nucleus. These patterns are not little tracks, they are structured possibilities. Matter remains stable because quantum mechanics restricts what electrons can do. The atom is not saved by tiny planets behaving well. It is saved by wave behavior, probability, and allowed states. So matter having a wavelength does not make matter unreal. It does not mean objects are imaginary, or that the floor beneath you is only pretending to be solid. The floor is solid because vast numbers of quantum particles, obeying quantum rules, combine into stable structures. The reality of matter is not weakened by its wave nature. If anything, it becomes richer. What once seemed like hard little objects turn out to be described by patterns that can spread, interfere, and settle into specific forms. This is one of the great shifts quantum physics asks for. The old image of matter as tiny solid beads is easy to picture, but it is not deep enough. At the smallest scales, matter is not merely stuff in motion, it's also wave-like structure, mathematical relationship, and probability shaped by physical law. Electrons can leave dots on a detector, but the pattern of many dots reveals a wave. Atoms can build solid objects, but their stability comes from quantum states. The familiar world remains real, steady, and touchable. It is simply built from something far more subtle than touch alone could ever reveal. The idea of the atom as a tiny solar system is one of those pictures that is hard to forget once it has entered the mind. A small nucleus sits in the middle, electrons circle around it like planets, and everything looks pleasingly neat. It is tidy, visual, and very useful for a first glance. It is also not really how atoms work. Like many simple science images, it points in roughly the right direction before quietly abandoning you at the edge of the truth. Atoms are not miniature star systems. The nucleus is not a little sun, and electrons are not tiny planets following clean circular roads through empty space. The real atom is more subtle. It is a quantum structure shaped by probability, energy levels, wave behavior, and restrictions on what electrons can do. This is not just a technical correction. It is the reason matter has stability, chemistry, color, and form. The atom is not a clockwork model. It is a set of allowed quantum possibilities arranged around a nucleus. Early atomic models borrowed from familiar images because scientists were trying to understand something they could not directly see. After Ernest Rutherford's gold foil experiment revealed that atoms contain a tiny dense nucleus, it made sense to imagine electrons moving around that nucleus in something like orbits. The comparison was tempting. The sun holds planets by gravity. A positively charged nucleus attracts negatively charged electrons by the electromagnetic force. From a distance, the analogy looks almost too convenient, like the universe had kindly decided to reuse the same design in different sizes. But classical physics quickly turns this tidy picture into a disaster. An electron is an electrically charged particle. According to classical electromagnetism, an accelerating charge should radiate energy. An electron moving in a circular orbit would constantly accelerate because its direction keeps changing. That means it should lose energy, spiral inward, and crash into the nucleus. If atoms really worked like tiny solar systems under classical rules, they should collapse almost immediately. Matter should not sit calmly in cups, tables, trees, and people. The fact that reality does not instantly fold into a tiny electromagnetic puddle is a fairly strong hint that something deeper is going on. Niels Bohr took an important step in 1913 by proposing a new model of the hydrogen atom. Bohr kept some of the orbit-like imagery, but added a radical rule. Electrons could only occupy certain allowed orbits, each with a specific energy. They could not spiral gradually downward through every possible path. Instead, they could jump between allowed energy levels by absorbing or emitting light. It was not yet the full modern picture, but it was a remarkable bridge between the old mechanical atom and the quantum atom. Bohr's model helped explain why hydrogen emits and absorbs light at particular frequencies. When an electron changes from a higher energy level to a lower one, it releases a photon with energy matching the difference between those levels. When it absorbs a photon of the right energy, it can move upward. Not just any photon will do, the energy has to fit. This is why atoms do not glow with every possible colour smeared together, but with specific spectral lines. Bohr had given physicists a way to understand atomic light as a set of quantum transitions rather than a continuous classical blur. Still, Bohr's model was not the final answer. It worked impressively well for hydrogen, the simplest atom, but struggled with more complicated atoms and deeper quantum behaviour. Modern quantum mechanics moved beyond electrons travelling in neat circular tracks. Instead of asking exactly where an electron is at every moment, it describes the electron with a wave function. From that wave function, physicists calculate probabilities. The electron is not pictured as a little bead following a known route. It is described through an orbital, a region of space where the electron is likely to be found if measured. An orbital is not an orbit with a slightly fancier name. That difference matters. An orbit is a path, like a planet moving around a star. An orbital is a probability distribution, a structured pattern around the nucleus. Some orbitals are roughly spherical, others have shapes that look more like dumbbells, clovers, or more complicated arrangements, although even those pictures are simplified ways of visualizing the mathematics. The electron is not smeared out like butter around the atom, which is merciful news for both physics and toast. Instead, the quantum state gives a pattern of possible detection, with some regions more likely than others. These orbitals are one reason atoms can form the rich chemistry of the world. The arrangement of electrons around a nucleus affects how an atom bonds, how it shares or transfers electrons, and how it interacts with light. The shapes and energies of electron states help determine why oxygen behaves differently from carbon, why sodium reacts eagerly with chlorine, and why noble gases are so famously unbothered. The atom's structure is not just a tiny hidden detail. It is the foundation of molecular shape, material properties, and the quiet architecture of everything solid enough to stub a toe on. Atomic spectra reveal this structure with extraordinary elegance. Each element absorbs and emits light at specific wavelengths, producing a pattern like a fingerprint. Hydrogen has one pattern, helium has another. Sodium, oxygen, iron, and neon each have their own spectral signatures. These patterns are not decorative. They are direct evidence that electrons in atoms have allowed energy levels. When light from a distant star is spread into a spectrum, those dark and bright lines can reveal what elements are present, even across enormous distances. The same quantum rules that shape a laboratory flame also help astronomers read the chemistry of stars. This is one of the loveliest consequences of atomic physics. The universe leaves barcodes in light. A glowing gas, a star's atmosphere, or a nebula can reveal its ingredients because atoms only trade energy in certain amounts. That means the tiny quantum structure of electrons becomes visible across space. Something happening around a nucleus far too small to see can write itself into starlight travelling for years, centuries, or far longer. The atom may be small, but it is not quiet. The stability of atoms, then, does not come from electrons obediently circling a nucleus like planets on invisible rails. It comes from quantum rules that allow only certain states. Electrons occupy structured wave-like arrangements. Their energies are restricted. Their behavior is shaped by probability rather than classical paths. They do not spiral into the nucleus because they are not little classical planets gradually losing orbital height. They are quantum objects, and quantum objects follow different rules. So the atom is both less mechanical and more beautiful than the old solar system picture suggests. The familiar diagram is useful as a doorway, but it should not be mistaken for the room. Inside the real atom, electrons are described by orbitals, energy levels, transitions, and probability patterns. Those rules explain why matter is stable, why elements have identities, why chemistry exists, and why light carries the fingerprints of atoms across the universe. The atom is not a tiny clockwork cosmos. It is a quantum structure, held together not by little planetary paths, but by the strange precision of allowed possibilities. By the time quantum physics reaches atoms and orbitals, one quiet idea has already begun to appear again and again. The smallest parts of nature do not always offer a single clear answer before they are measured. An electron in an atom is not described as a tiny object following a known path. Light can spread as a wave of possibility and then arrive as one detected photon. Matter can leave individual marks, while still producing interference patterns over many repeated trials. The small world seems to speak in probabilities. That can sound, at first, like a weakness. Probability is often what people use when they do not know enough. A weather forecast gives a chance of rain because the atmosphere is complicated. A shuffled deck of cards feels uncertain because nobody has looked at the top card yet. A person searching for their keys may say there is a good chance they are on the kitchen counter, because that is where the keys usually go, even though the keys themselves are not undecided. They are somewhere. The ignorance belongs to the person, not the keys. Quantum probability is deeper than that. It is not just a fog placed over a perfectly definite classical story. It is built into the way the theory describes nature. The wave function is the central mathematical object used to describe a quantum system. It is not a photograph of a particle, and it is not a little map showing exactly where everything is hiding. Instead, it contains information about the possible outcomes that could appear when a measurement is made. For an electron, the wave function can describe the chances of finding it in different regions of space. For a photon, it can describe possible paths, polarizations, or energies, depending on the experiment. It is a compact and powerful description of what the system may reveal. This is one reason quantum physics can feel so slippery in ordinary language. A wave function is not quite a physical wave in the everyday sense, like a ripple moving across water. It can behave mathematically like a wave, spreading, overlapping, and interfering. But what it gives directly are probabilities. When physicists calculate with the wave function, they're not usually predicting one guaranteed result. They are calculating the structure of possible results and how likely each one is to appear. It is like nature handing over a beautifully detailed menu while refusing to say exactly which dish will arrive until the measurement is made. Max Born played a crucial role in making sense of this. In the 1920s, Born argued that the wave function should be understood probabilistically. More specifically, the mathematics of the wave function could be used to calculate the probability of different measurement outcomes. This was a major shift. Earlier physics had often aimed to predict exact motion from exact starting conditions. If the position and motion of a planet were known well enough, its future path could be calculated. If a ball was thrown with a certain speed and angle, its path could be predicted with ordinary classical methods. Quantum mechanics seemed to be saying something different. Born's interpretation did not make quantum physics less scientific. It made it more honest. Experiments were showing that individual quantum events could not always be predicted with certainty, even when the overall conditions were controlled with great care. What could be predicted was the pattern over many events. Born's rule gave physicists a way to connect the wave function to observed reality. The wave function did not simply tell a hidden story of where the particle really was all along. It gave probabilities for where it might be found. That idea became one of the foundations of quantum mechanics, and also one of the reasons the theory still feels philosophically unsettling. The difference between quantum probability and ordinary uncertainty is important. Imagine a coin hidden under a cup. It is either heads or tails. The observer may not know which, but the coin has already landed. The uncertainty is personal. It belongs to the person who has not looked. Many classical situations are like this. A card is already in the deck. A lost object is already somewhere. A dice result, once rolled and covered, is already fixed. Probability in those cases often describes limited knowledge about a definite situation. Quantum probabilities do not always work that way. Before measurement, a quantum system may not possess the measured property in a simple pre-existing form, at least not in the straightforward everyday sense. The quantum state can contain several possible outcomes, and the act of measurement gives one result from that structure. This does not mean consciousness is magically inventing the world, or that anything can happen just because someone feels strongly about it. The probabilities are tightly controlled by the wave function and the physical setup. Quantum weirdness is not a blank check. Nature remains extremely strict, even when it is being strange. Repeated experiments reveal this strictness beautifully. A single radioactive atom may decay at an unpredictable moment. One photon passing through an experiment may land at a location that cannot be known in advance. One electron measured in a certain way may produce one result from a set of possibilities. But repeat the experiment many times, under the same conditions, and a clear statistical pattern emerges. The individual event may resist certainty, but the collective behavior becomes sharply predictable. This is one of the quiet miracles of quantum physics. It gives up exact prediction in one place and returns precision somewhere else. The double-slit experiment is a lovely example. A single particle may appear as one dot on a screen. That dot alone can look almost random. Another particle arrives, then another, and each one leaves a small individual mark. But after many arrivals, the dots build into an interference pattern. The pattern was not placed there by one particle alone. It emerges from the probabilities encoded in the quantum state. Each particle lands somewhere definite when detected, yet the distribution of many detections follows the wave-like structure of possibility. It is as though nature is unpredictable in the details, but deeply disciplined in the design. This is why quantum physics is not chaotic guesswork. It is not a shrug wearing a lab coat. It is one of the most precise scientific frameworks ever created. Its predictions have been tested in atomic physics, particle physics, chemistry, materials science, electronics, and precision measurement. The uncertainty of individual outcomes does not make the theory vague. In fact, the probabilities are often calculated with extraordinary accuracy. The strange part is not that quantum physics fails to predict. The strange part is what kind of prediction it offers. At the smallest scales, nature seems to trade some of the certainty of classical physics for a deeper statistical order. The wave function does not usually say this exact thing will happen in this exact way. It says these are the possible outcomes and these are their probabilities arranged by the structure of the quantum state. That may feel less satisfying at first because the human mind likes a clear little story with a beginning, middle, and neatly labelled electron. But the universe is not required to provide bedtime-level narrative convenience, even during a bedtime science video. So probability is not an afterthought in quantum physics. It is woven into the theory from the beginning. The small world is not merely hidden from view, waiting for better instruments to reveal a perfectly ordinary mechanical script underneath. It behaves according to rules in which possibility is structured, measured outcomes are definite, and repeated trials reveal patterns of astonishing reliability. Quantum physics is strange because it replaces simple certainty with disciplined probability. It does not make reality loose, it makes reality precise in a way that everyday intuition did not expect. Probability already makes the quantum world feel less certain than the familiar world of falling stones and swinging doors. But uncertainty goes even deeper. It is not only that some outcomes cannot be predicted exactly before measurement, it is that certain properties cannot both be sharpened without limit at the same time. At small scales, nature does not always allow every detail to be pinned down together, no matter how careful the experiment becomes. This is one of the easiest quantum ideas to misunderstand, partly because the word uncertainty sounds ordinary. In everyday life, uncertainty usually means someone does not know enough. The weather is uncertain because the atmosphere is complicated. A misplaced phone is uncertain because it has slipped into the sofa again, where all small objects apparently migrate. A person might be uncertain because they have not checked, measured, or looked closely enough. But the uncertainty in quantum physics is not simply a confession that the equipment is poor, or that the scientist forgot to bring a better ruler. Werner Heisenberg's uncertainty principle says that certain pairs of properties cannot both be known with unlimited precision. The most famous pair is position and momentum. Position describes where something is. Momentum describes how much motion it has, linked to its mass and velocity. In classical physics, at least in principle, a particle can have a perfectly definite position and a perfectly definite momentum at the same time. If the instruments are good enough, the story can be sharpened. Measure more carefully, calculate more precisely, and the picture becomes clearer. Quantum physics changes that expectation. For a particle such as an electron, the more tightly its position is defined, the less tightly its momentum can be defined. And the more tightly its momentum is defined, the more spread out its position becomes. This is not a minor inconvenience. It is not a smudge on the lens of reality. It is a limit written into the theory itself. Nature does not hand over both answers with perfect sharpness. It allows a trade-off, as though the small world has its own quiet rule about how much exactness can be packed into a single description. A common but incomplete explanation says that measuring a particle disturbs it. There is some truth in the broader idea that measurement in quantum physics involves interaction. To find something, something else must usually interact with it. Shine light on an electron, and the light can affect it. Touch a delicate system with a measuring device, and the system may change. But this does not fully explain Heisenberg's uncertainty principle. The principle is not merely about clumsy interference. It would be far less interesting if it were only a warning label reading, "Please stop poking the electron." The deeper reason comes from the wave-like nature of quantum states. A wave that is spread out over a large region can have a well-defined wavelength. If a particle is described by a wave with a very clear wavelength, then its momentum can be quite sharply defined, because wavelength and momentum are linked. But a wave that stretches broadly across space does not point to one precise position. It is spread out. The particle's location becomes less definite. To make the position sharper, the wave must be compressed into a smaller region. Compressing a wave into a smaller region requires combining many different wavelengths. This is a key idea. A sharply localized wave packet is not made from one simple, perfect wave. It is built from a mixture. That mixture of wavelengths means a mixture of possible momenta, so the particle can become more definite in position only by becoming less definite in momentum. The uncertainty is therefore not an accident caused by bad measurement. It arises from the mathematics of waves themselves. Once matter is described by quantum waves, the trade-off is built in. There is a calm way to picture it, though no picture is perfect. Imagine a musical note. A long, steady tone can have a very clear pitch because it continues long enough for the frequency to be well defined. But if the sound is cut into a tiny click, its timing becomes sharp while its pitch becomes less precise. The more exactly the sound is localized in time, the less it behaves like one pure tone. Quantum uncertainty has a similar mathematical flavor, though it applies to physical properties like position and momentum. The universe is not being vague. It is obeying wave mathematics with absolute seriousness. A particle with a sharply defined position must therefore be described by a spread of wavelengths. Those wavelengths correspond to different momenta, which means the particle's motion cannot be assigned one perfectly exact value. If that sounds strange, it is because everyday objects are enormous compared with quantum scales. A thrown ball is made from vast numbers of particles, and its quantum uncertainties are so tiny relative to its size and motion that they disappear from ordinary experience. A tennis ball does not become a mist of mystery on its way across a court. It remains very helpfully tennis ball-like. But for electrons, atoms and other small systems, the uncertainty matters. It affects how particles behave in confined spaces, how atoms are structured, and how matter resists collapse. An electron trapped near a nucleus cannot simply have both a perfectly fixed position and no uncertain motion. Confinement changes the range of possible momentum. The smallness of the atom is tied to the wave-like behavior of its electrons. The uncertainty principle is not just a philosophical curiosity. It helps explain why atoms have size, why electrons occupy quantum states, and why matter does not collapse into featureless density. There is also an uncertainty relationship between energy and time, though it must be handled with more care than position and momentum. In quantum physics, short-lived states have an inherent spread in energy. If a state exists only briefly, its energy cannot be defined with perfect sharpness. This appears in effects such as spectral line widths, where light emitted by atoms is not always an infinitely narrow frequency, but has a small natural width linked to the lifetime of the excited state. The shorter the lifetime, the broader the energy spread. This energy-time uncertainty is sometimes described too loosely, as if nature is casually borrowing energy and hoping nobody notices. That image can be entertaining, but it can also mislead. The more careful point is that quantum processes involving duration and energy have limits on how sharply both can be specified. A very brief event does not produce an infinitely exact energy signature. The relationship shows up in real measurable phenomena, especially in atomic and particle physics, where unstable states and excited systems leave traces of their lifetimes in the spread of their energies. Uncertainty, then, is not a failure of knowledge in the ordinary sense. It is not simply that physicists have not yet built a sufficiently heroic microscope. It is a structural feature of the quantum world. Certain properties are linked in such a way that sharpening one necessarily spreads the other. The limit is not imposed from outside the system. It comes from the form of quantum states themselves. And strangely, this limit is part of what allows the world to be stable. If electrons could sit perfectly still in perfectly exact locations, atoms would not have the structure they do. If quantum states did not have wave-like restrictions, chemistry would not have its familiar architecture. Matter would not hold itself together in the same way. The uncertainty principle can sound like a loss, as though nature has taken away exact knowledge. But it is also a source of structure. It helps make atoms possible, and therefore molecules, materials, bodies, planets, and quiet rooms full of ordinary things that feel wonderfully definite, even though their foundations are not. Uncertainty leaves the quantum world looking gently unpinned, not chaotic, not lawless, but less fixed than everyday intuition expects. A particle may not have a perfectly sharp position and a perfectly sharp momentum at the same time. A quantum state may hold a range of possibilities rather than one neatly completed answer, and from there the next strange idea begins to appear. Sometimes nature does not seem to choose one option until an interaction forces the question. This is where superposition enters. It is one of the most famous ideas in quantum physics, and also one of the easiest to exaggerate. Superposition does not mean that anything can be anything, or that reality is a vague soup of imagination waiting for a person to look at it. It means that a quantum system can be described as a combination of different possible states. Those possibilities are not merely ordinary hidden alternatives, like a coin already lying heads or tails under a cup. They are part of the quantum description itself. A quantum system in superposition is not simply concealing one normal answer, while the observer remains ignorant. In many experiments, treating the system as if it already had one definite classical value gives the wrong prediction. The system must be described as a combination of possibilities. An electron, for example, may be in a superposition of different positions, different energy states, or different spin states depending on the situation. A photon may be described as taking a combination of possible paths through an experiment. That sounds peculiar, because the ordinary world trains the mind to expect objects to make clear choices. A door is open or closed, a lamp is on or off, a biscuit is present or has mysteriously vanished, usually because someone in the house has behaved with quiet efficiency. But quantum systems are not just tiny versions of familiar objects. Their state can include multiple alternatives at once, and those alternatives matter. They are not optional decorations in the mathematics. They affect what happens next. When measurement occurs, one outcome is found, but before that measurement, the quantum state may genuinely require a combination of possibilities to describe it correctly. Superposition is responsible for interference, one of the clearest signs that quantum possibilities are more than ordinary guesses. If a quantum object could only be in one ordinary hidden state, the patterns seen in interference experiments would be very difficult to explain. But when different parts of a quantum state can overlap, they can combine. Some possibilities reinforce one another, making certain outcomes more likely. Others cancel one another, making certain outcomes less likely or even absent. The resulting pattern is not just a blur of confusion. It is a structured effect produced by the way quantum possibilities interact. This is why the double-slit experiment is so powerful. A particle may be detected as one localized mark on a screen, but the distribution of many marks forms an interference pattern. That pattern appears because the quantum state includes possible paths through both slits, and those possibilities interfere. The particle is not behaving like an ordinary pellet that simply chooses one slit, while the other slit is irrelevant. The whole experimental arrangement shapes the wave-like structure of the quantum state. Superposition gives the particle a kind of mathematical openness before detection, and interference reveals that openness in the final pattern. The phase of a quantum state is one of the hidden-looking details that makes superposition work. Phase is not something directly visible like colour, size or brightness. It is more like the timing or alignment of a wave. Two waves may have the same size and shape, but if their crests and troughs line up differently, they combine differently. When waves are in step, they can strengthen each other. When they are out of step, they can cancel. In quantum physics, phase controls how different parts of a superposition interfere. This means quantum possibilities are not just sitting side by side like items on a menu. They have relationships. The phase between them determines how they combine when the system evolves or when an experiment brings the possibilities together. A change in phase can shift an interference pattern. It can alter probabilities. It can turn one likely result into an unlikely one. This is one reason quantum physics is so precise despite sounding strange in words. The strangeness is not vague. It has angles, amplitudes, phases, and equations. The universe may be odd at small scales, but it is odd with excellent bookkeeping. No discussion of superposition can avoid Schrödinger's cat, because the cat has wandered permanently into the public imagination, probably against its will. Erwin Schrödinger proposed the famous thought experiment in 1935 to highlight how strange quantum ideas become if they are extended too simply into the everyday world. In the scenario, a cat is imagined inside a sealed box with a device linked to a quantum event, such as radioactive decay. If the event occurs, the device causes one outcome. If it does not, another. The cat becomes entangled with the quantum event in the logic of the thought experiment. The point was not that real cats casually lounge around in a condition of being half alive and half dead. Schrödinger was not offering a pet care recommendation, which is just as well. He was showing that applying quantum superposition to large everyday objects raises deep questions about measurement, observation, and the boundary between the quantum and classical worlds. A single atom can be placed in a superposition and tested experimentally. A cat, however, is warm, complex, constantly interacting with its surroundings, and made of an enormous number of particles. Environmental interactions rapidly destroy the delicate interference effects that make visible superpositions possible. This does not make the cat example useless. It remains powerful because it exposes the measurement problem. Quantum theory can describe superpositions very well, but the everyday world seems full of definite outcomes. At some point the possible becomes the observed. Different interpretations of quantum mechanics explain that transition in different ways. Some focus on measurement, some focus on branching realities, some focus on hidden variables or information. But the practical fact remains: superposition is experimentally real at small scales, and its extension into the large world is where the deepest conceptual puzzles begin. Superposition is not fantasy. It is not indecision. It is not a mystical invitation to believe that all ordinary contradictions are secretly true. It is a measurable feature of quantum systems. Without it, interference would not make sense. Quantum computing would lose its foundation. Atomic and molecular behavior would be hard to understand. The delicate behavior of photons, electrons, atoms, and other small systems depends on the ability of quantum states to combine possibilities in precise ways. The important thing is to keep the idea both strange and grounded. A quantum system in superposition is not behaving like a human unable to choose between two desserts. It is described by a state that genuinely includes more than one possible outcome, with amplitudes and phases that determine how those possibilities interact. When measured, a definite result appears. Before measurement, the structure of possibility matters physically. Superposition is one of the ways quantum physics shows that reality's smallest layer is not made from tiny everyday objects with tiny everyday habits. It is made from states, relationships, and possibilities that only become familiar after the mathematics has taught intuition to be a little more humble. Superposition naturally leads to one of the most stubborn questions in quantum physics. If a quantum system can be described as a spread of possibilities, why does an experiment produce one definite result? A detector does not usually report a poetic blend of maybe this and maybe that. It clicks in one place. A measuring device gives one reading. A screen records one mark. The quantum state may contain a range of possible outcomes, but the world of experience arrives as something more specific. This is the puzzle of measurement. It is not just a technical question about laboratory equipment, although laboratory equipment is very much involved. It is a question about how the smooth mathematics of quantum possibilities becomes the definite world of observed results. Quantum theory is extraordinarily good at predicting the probabilities of those results. It tells physicists what can happen and how likely each outcome is. But the deeper question of what exactly happens during measurement has remained one of the most debated parts of the theory. In quantum physics, measurement connects a spread of possible outcomes to one observed result. Before measurement, a system may be described by a superposition of states. After measurement, the experiment has produced something definite. An electron is detected in a certain region. A photon is absorbed by a particular atom. A spin measurement gives one of the allowed outcomes. The shift from many possible results to one actual result is why measurement sits at the heart of the measurement problem. This does not mean that measurement is mysterious because the equipment is poorly understood. Quite the opposite. Detectors, screens, magnets, lasers, and electronics can be described with extraordinary precision. The puzzle is not that scientists are wandering into the laboratory saying, well, the machine did something dramatic and now everyone is upset. The puzzle is that quantum theory has a very clear way of describing the evolution of possibilities and a very clear way of calculating measurement probabilities, but the interpretation of the moment one result becomes actual is still not universally agreed upon. A common misunderstanding is that quantum measurement requires a conscious observer. It does not. A measuring device does not need a person staring at it, stroking their chin and whispering, "I hereby observe you." In physics, measurement can mean any interaction that records, reveals, or amplifies information about a system. A photon hitting a photographic plate, an electron triggering a detector, or an atom interacting with its environment can all count as measurement-like processes. The key point is not human awareness. The key point is physical interaction that leaves information behind. This distinction matters because quantum physics is often surrounded by tempting but misleading phrases. The idea that consciousness collapses reality may sound dramatic, but it is not required by standard experimental practice. The moon does not wait politely for someone to glance upward before continuing to exist. The laboratory record does not need a human mind to become a physical record. Measurement is about the system becoming correlated with something else in a way that makes an outcome available in the world. A detector can sit in a room, record an event, and preserve that record long before anyone checks it. Decoherence helps explain why quantum possibilities stop visibly interfering when systems interact with their environment. In a delicate quantum experiment, different parts of a superposition can maintain a relationship with each other. Their phases remain coordinated, allowing interference to appear. But when a system interacts with many surrounding particles, air molecules, photons, vibrations, or any messy environmental influence, that delicate phase relationship becomes effectively scrambled into the wider environment. The superposition has not simply been erased in the most naive sense, but its interference becomes practically impossible to observe. This is one reason everyday objects do not seem to behave like obvious quantum superpositions. A dust grain floating in sunlight is constantly being struck by photons and air molecules. A warm object is interacting internally and externally in an enormous number of ways. A cat, being warm, furry, complicated, and probably unimpressed, is interacting with its environment far too strongly to preserve the kind of delicate coherence seen in isolated quantum systems. Decoherence explains why large objects appear classical. Their quantum alternatives lose the ability to interfere with one another in any visible way. The word classical here means the ordinary style of behavior described by pre-quantum physics. Objects have fairly definite positions. Events seem to happen in one way. Chairs do not noticeably spread through doorways as waves of possibility, which is considerate of them. Decoherence shows how this classical appearance can emerge from quantum systems interacting with their surroundings. It explains why the fragile interference seen in small, carefully isolated systems disappears when those systems become entangled with a large, noisy environment. But decoherence does not solve every philosophical question about measurement. It explains why interference becomes unavailable and why different outcomes stop communicating with each other in practice. It helps show how the world comes to look definite. Yet some physicists and philosophers argue that it does not fully explain why one particular outcome is experienced rather than another, or what exactly counts as the final physical story. Different interpretations of quantum mechanics answer that question differently. Some accept collapse as a fundamental process. Some say all outcomes persist in branching worlds. Some reshape the theory in other ways. This is where quantum measurement remains both practical and profound. In the laboratory, the rules work. Scientists can calculate probabilities, run experiments, and build technologies with breathtaking accuracy. Measurement outcomes follow the patterns quantum theory predicts. But when asking what measurement means at the deepest level, the answer becomes less settled. The mathematics is not failing. It is the interpretation that becomes difficult. Quantum physics is a little like receiving an instruction manual that works perfectly, while somehow leaving out a page titled "What This All Means." Still, the uncertainty in meaning should not be confused with uncertainty in usefulness. Measurement is central to everything quantum physics does. Without measurement, there would be no way to connect the theory to experimental reality. Every spectral line, detector click, interference pattern, and atomic transition becomes evidence because something has interacted, recorded, and produced an outcome. The theory's power lies in the way it links the unseen structure of quantum states to the visible results of experiment. So measurement changes the story because it is where possibility meets record. A quantum system may evolve as a spread of potential outcomes, shaped by amplitudes and phases. A measurement produces one result from that spread. Decoherence explains why the delicate quantum relationships that allow interference become hidden when systems interact with their environments, and why the everyday world appears stable, definite, and classical. Yet the deeper meaning of that transition remains one of the great unresolved questions in physics. Quantum measurement sits at the boundary between possibility and actuality. It is not magic, and it is not a trick of the human mind. It is a physical process with measurable consequences, described by a theory of extraordinary precision. But it also touches the place where the theory's practical success becomes philosophically strange. The detector clicks, the mark appears, the record is made, the mathematics works beautifully. And somewhere inside that simple event, quantum physics leaves one of its quietest and deepest questions still open. Once measurement enters the story, quantum physics becomes stranger in a new way. It is already surprising enough that a single quantum system can be described through probabilities, superpositions, and outcomes that only become definite when measured. But entanglement goes further. It says that two or more quantum systems can be described by one shared state, even when the parts are separated. The relationship between them becomes part of the physics, not just an afterthought. This is where the ordinary idea of separateness begins to wobble slightly. In daily life, separate objects usually have separate properties. One glove can be in a drawer, another can be in a coat pocket, and if one is left-handed, the other is right-handed simply because the pair was already arranged that way. Nothing mysterious needs to pass between them. Quantum entanglement is more subtle than that. It is not just about discovering matching properties. It's about systems whose shared quantum state can be better defined than the individual parts on their own. Entangled particles are described by a shared quantum state. That means the whole system can have a definite relationship, even if each individual particle does not have its own separate definite property before measurement. For example, two particles may be entangled so that their measured results are linked. If one is found with a certain outcome, the other will be found with a related outcome, even if the particles are far apart. The relationship is built into the state of the pair. This does not mean the particles are secretly whispering across space like tiny conspirators. It means quantum mechanics describes them as one connected system, not as two fully independent objects carrying complete pre-written instructions. That is the part that makes entanglement so difficult to translate into everyday language. The whole as a kind of quantum description that cannot be reduced to two ordinary separate descriptions. The particles may be distant, but their possible outcomes are tied together through the structure of the shared state. Albert Einstein was deeply uncomfortable with this implication. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published an argument now known as the EPR argument. They used entanglement to suggest that quantum mechanics might be incomplete. Their concern was not that quantum mechanics failed as a calculating tool. It clearly worked. Their concern was that the theory seemed to imply strange connections between distant systems, or else that it did not fully describe all the real properties those systems possessed. Einstein famously disliked the idea that quantum mechanics abandoned the kind of definite reality he expected from a complete physical theory. He hoped there might be hidden variables, deeper pieces of information not included in standard quantum mechanics, which would restore a more ordinary picture. In that view, entangled particles might already carry definite properties from the moment they separate, like sealed envelopes containing matching instructions. The measurement would simply reveal what was already there. This would preserve a more familiar kind of locality, where objects are only directly influenced by their immediate surroundings. For a while, this debate seemed partly philosophical. Quantum mechanics predicted the results of experiments extremely well, while Einstein and others wondered whether a deeper theory might explain those results in a more intuitive way. Then John Bell changed the conversation. In the 1960s, Bell showed that the disagreement could be tested. He developed Bell's theorem, which revealed that quantum mechanics and local, hidden variable theories do not always make the same statistical predictions. That was a remarkable turning point. Bell's work meant the question was no longer only about taste, interpretation, or which picture felt more reasonable. It became an experimental question. If particles merely carried hidden local instructions, their measurement results should obey certain limits, now called Bell inequalities. If quantum mechanics was right, entangled particles could violate those limits. This gave physicists a way to ask nature directly whether the world followed Einstein's preferred local hidden variable style, or the stranger quantum pattern. Bell test experiments have strongly supported quantum mechanics. Over many decades, increasingly careful experiments have measured entangled particles and found correlations that violate Bell inequalities. These correlations cannot be explained by simple local hidden variables. The experiments have become more refined over time, closing important loopholes and strengthening the conclusion. Nature appears to follow the quantum prediction, not the more comfortable classical-style picture in which every outcome was simply written down locally in advance. This is one of the most important experimental achievements in modern physics. It shows that entanglement is not a poetic metaphor. It is not a mystical mood. It is a real, measurable feature of quantum systems. The correlations between entangled particles are stronger than ordinary local hidden variable explanations allow. Quantum mechanics does not merely sound strange in this area. It has been repeatedly tested, and the strange answer keeps surviving. But it is just as important not to overstate what entanglement does. Entanglement does not allow faster-than-light messaging. A person measuring one particle cannot choose the result in a way that sends a controllable signal to someone measuring the other particle. Each individual result still contains quantum randomness. Only when the two sets of results are later compared through ordinary communication do the correlations become visible, and that ordinary communication cannot travel faster than light, so entanglement does not break relativity by becoming a cosmic text message service. It does not allow instant phone calls across the galaxy, which is probably for the best, because the roaming charges would be emotionally significant. The link between entangled particles is not a usable signal moving through space. It is a correlation built into the shared quantum state. The universe allows the pattern, but not the shortcut. That distinction is essential. Entanglement is deeply strange, but it is not a loophole for sending information faster than light. The deeper lesson is that quantum separateness is not as simple as everyday separateness. In the familiar world, it feels natural to imagine that objects carry their own properties independently. A cup has its shape. A stone has its weight. A coin under a hand is already heads or tails. But in quantum physics, systems can be connected in ways that make the shared state more fundamental than the separate descriptions of the parts. The relationship itself becomes part of what is real. Entanglement now sits at the heart of quantum information science. It is used in quantum communication, quantum computing research, and tests of the foundations of physics. What began as a challenge to the completeness of quantum mechanics has become one of its most powerful confirmed features. Einstein saw entanglement as a sign that something was missing. Modern experiments suggest that what was missing was not necessarily a hidden classical mechanism, but a willingness to accept that the quantum world does not divide itself as neatly as the human mind expects. So entanglement makes separateness complicated. It does not dissolve distance, and it does not turn the universe into magic. It does not let particles chat faster than light, or prove that everything is secretly controlled by thought. What it shows is quieter and more precise. Two particles can belong to one quantum state, and the measurements made on them can reveal correlations that no simple local hidden variable story can explain. At the deepest level, the world is not always assembled from independent pieces carrying fully private properties. Sometimes the relationship comes first, and the separate parts only make complete sense within the whole. Entanglement shows that quantum systems can share relationships in ways that feel deeply unfamiliar, but those relationships only become visible when something is measured, and one of the most important things that can be measured is spin. The word sounds simple. It suggests something turning, rotating, or whirling around like a tiny planet, a spinning top, or a coin wobbling on a table. Unfortunately, quantum physics has a long tradition of borrowing ordinary words and then quietly making them much stranger. Spin is one of the clearest examples. It is real, measurable, and absolutely central to modern physics. It affects how particles behave, how atoms arrange themselves, how magnets work, and how matter builds structure. But it is not spin in the everyday sense. An electron is not a tiny ball turning around its own axis like a miniature moon. If that image appears in the mind, it is useful only as a very rough doorway, and even then it should probably be asked to wipe its feet before coming in. Quantum spin is an intrinsic property of particles. Intrinsic means it belongs to the particle itself, not because the particle is made from smaller parts visibly rotating, but because spin is part of its quantum identity. An electron has spin in the same deep way it has electric charge and mass. These are not optional accessories. They are part of what makes an electron an electron. The word spin was chosen because the property gives particles angular momentum, and in ordinary physics, angular momentum is often associated with rotating objects. But at the quantum level, the comparison becomes misleading if taken too literally. The problem with imagining an electron as a spinning ball is that an electron, as far as modern experiments can tell, does not have a little surface that could rotate like a tennis ball. It behaves as a point-like particle in the standard model, with no known internal structure at accessible scales. Its spin is quantized, meaning it can only appear in certain allowed forms when measured. So quantum spin is not a tiny mechanical motion hiding inside the particle. It is a built-in quantum property whose effects show up in experiments, even though the everyday image behind the name does not really apply. Spin helps determine how particles behave in magnetic fields. Particles with spin can have magnetic moments, meaning they respond to magnetic fields in particular ways. An electron, for example, acts a little like a tiny magnet, though again, the word tiny needs careful handling. This magnetic behavior is one reason spin matters so much in atoms and materials. When a particle moves through a magnetic field, its spin can affect how it is deflected, how its energy changes, and how it interacts with its surroundings. Spin also helps determine how particles combine. In quantum physics, the total spin of a system matters. Particles can pair, align, oppose one another, or combine into larger structures with particular quantum properties. The spin of electrons helps shape the arrangement of electrons in atoms. The spin of nuclei is important in technologies such as magnetic resonance imaging. The spin of particles is also tied to deeper rules about whether they belong to families called Fermions or bosons, which affects whether particles build matter or gather together in shared states. A small-sounding property turns out to have enormous consequences. One of the most famous experiments revealing spin-related behavior is the Stern-Gerlach experiment, performed in the early 1920s by Otto Stern and Walter Gerlach. In the experiment, a beam of silver atoms was sent through a non-uniform magnetic field. If the atoms behaved like tiny classical magnets, with all possible orientations, the beam should have spread into a continuous smear. Instead, it split into distinct paths. The result showed that the relevant angular momentum was quantized. The atoms did not produce every possible outcome. They separated into specific allowed results. This was a deeply important moment because it showed discrete quantum behavior in a very direct way. The measuring device did not reveal a smooth range of values but a split. In later understanding, the experiment became strongly associated with spin and the discrete outcomes of quantum measurement. It helped make clear that some quantum properties do not come in a continuous set of options. When measured in a particular direction, spin can give specific results, such as up or down rather than any value in between. The universe, once again, refused to behave like a smooth dimmer switch and preferred something closer to a very strict two-option menu. That does not mean the particle itself is simply carrying a little arrow already pointing up or down in the ordinary sense. The direction chosen for measurement matters. A spin state can be prepared in relation to one axis and then measured along another, producing probabilistic outcomes. This is where spin becomes a beautiful example of how quantum properties differ from classical ones. A classical spinning object can have a definite orientation in space. A quantum spin state is described differently. It can be in a superposition relative to different measurement directions, and the result depends on how the question is asked. Spin is also central to magnetism. In many materials, magnetic behavior depends heavily on the arrangement of electron spins. Electrons act as tiny sources of magnetism, and when many electron spins align in the same direction, their magnetic effects can reinforce one another. This is part of what happens in ferromagnetic materials such as iron. The individual quantum properties of countless electrons combine into a large-scale magnetic effect strong enough to hold a note to a fridge, which is a very humble use of deep quantum order. In other materials, electron spins may pair off or align in opposing ways so that their magnetic effects cancel. Some materials are weakly attracted to magnetic fields, some are repelled, and some can preserve strong magnetization. The differences arise from electron arrangements, spin alignment, atomic structure, and interactions between neighboring atoms. Magnetism may feel like a familiar everyday force, especially when a fridge magnet is doing its one simple job with quiet dignity. But beneath that small domestic miracle is quantum spin. Ordinary magnets are not ordinary at all once examined closely. Spin is also essential in modern technology and scientific measurement. Magnetic resonance imaging uses the spin of atomic nuclei, especially hydrogen nuclei in the body, and how those spins respond to magnetic fields and radio waves. Quantum computing research often uses spin-like two-state systems as possible qubits. Spintronics, a field of electronics, explores how electron spin as well as electric charge can be used to store and process information. The property that began as a strange quantum label now appears in medicine, material science, data storage, and precision experiments. So spin is a perfect example of quantum language. It uses a familiar word, but the familiar image only carries part of the way. Spin is not really spinning in the everyday mechanical sense. It is an intrinsic quantum property, measurable through experiments, linked to angular momentum, magnetic behavior, particle identity, and the structure of matter. It helps determine how particles respond to magnetic fields, how atoms arrange themselves, and how materials become magnetic. The deeper lesson is that quantum physics often speaks with borrowed words, because human language was built for trees, stones, rivers, weather, and mildly inconvenient furniture, not for electrons. Words like spin, wave, particle, and orbit can guide the imagination, but they can also mislead it. Spin reminds us that the small world is not simply a smaller copy of the large one. It has properties that are real and precise, but not always picturable in ordinary terms. The electron is not a tiny spinning bead. It is something stranger, quieter, and more exact. A quantum object carrying a property that helps shape the magnetic, material, and technological world around us. Spin quietly opens a doorway into one of the most important divisions in the quantum world. Once particles have intrinsic spin, that spin helps place them into broad families with very different behaviors. These families are not just labels added for neatness. They help explain why matter takes up space, why atoms have structure, why forces can be exchanged, and why the universe is not simply a bland mist of identical quantum ingredients. The two great families are fermions and bosons. Their names sound a little like rival teams in an extremely niche sporting event, but their difference is fundamental. Fermions are the particles most closely associated with building matter. Bosons are often associated with carrying forces or with special collective behaviours where many particles can act together in the same state. The contrast between them is one of the hidden reasons reality has both solidity and motion, both structure and interaction. Fermions include electrons, quarks, protons, and neutrons. Strictly speaking, protons and neutrons are not elementary particles, because they are made of quarks bound together by the strong force, but they still behave as fermions. These are the particles most directly involved in making ordinary matter. Electrons surround atomic nuclei. Protons and neutrons make up those nuclei. Quarks are the deeper ingredients inside protons and neutrons. If matter is the furniture of the universe, then fermions are some of its most important building materials. What makes fermions especially important is that they do not like sharing the same quantum state. This is not a matter of personality. Electrons are not being rude. They do not form queues out of stubbornness. The rule comes from quantum mechanics and the kind of spin fermions have. Fermions have half-integer spin, such as 1/2, 3/2, and so on. That spin category gives them a special mathematical behaviour when identical particles are exchanged, and from that behaviour comes one of the most important rules in all of physics, the Pauli exclusion principle. Bosons behave very differently. Bosons include particles such as photons, which are the quanta of the electromagnetic field, and gluons, which help carry the strong force between quarks. The Higgs boson is associated with the Higgs field, and the W and Z bosons carry the weak force. Bosons have integer spin, such as 0, 1, or 2. That difference in spin category changes how they behave when particles are grouped together. Unlike fermions, bosons are perfectly happy to share the same quantum state. This sharing behaviour makes bosons central to forces and collective quantum effects. Photons can gather into coherent states of light, which is part of what makes lasers possible. Gluons help hold quarks together inside protons and neutrons. Bosons can also appear in systems where many particles act together in the same state, producing behaviour that looks very different from ordinary matter. If fermions are often the builders of structure, bosons are often the messengers, carriers, and coordinators of interaction. A slightly overworked job description perhaps, but an impressive one. The Pauli exclusion principle says that no two identical fermions can occupy exactly the same quantum state at the same time. This rule is one of the great quiet architects of the universe. Without it, electrons in atoms would all collapse into the lowest available energy state. Chemistry would be radically different, which is a polite way of saying that chemistry as we know it would not really exist. Atoms would not have the layered electron structures that produce the periodic table. The variety of elements would lose much of its pattern and personality. Because electrons cannot all crowd into the same state, they fill available states in a structured way. This creates shells and subshells around atoms. Those arrangements help determine how atoms bond, how they react, and what kinds of molecules they form. Oxygen behaves differently from nitrogen because its electrons are arranged differently. Sodium and chlorine form table salt because their electron structures make a certain exchange energetically favourable. Carbon can build long chains and complex molecules partly because of its electron configuration. Beneath all of this sits the refusal of identical fermions to pile into the same quantum state. The Pauli exclusion principle also helps explain why matter resists being squeezed too much. The particles in matter cannot simply all collapse into the exact same state. At ordinary scales, this contributes indirectly to the solidity of objects. When you press your hand against a table, the atoms in your hand and the atoms in the table do not simply pass through one another. Electromagnetic forces are crucial here. but the structure of electron states, shaped by the Pauli exclusion principle, is also part of the deeper explanation. Solid matter is not solid because atoms are tiny hard balls touching like marbles. It is solid because quantum rules and forces create stable arrangements that resist overlap. Bosons, by contrast, can gather together in the same state, and this opens the door to very different phenomena. Laser light is a beautiful example. In ordinary light, photons may have many different phases, directions, and frequencies mixed together. In a laser, photons are produced in a highly coordinated way, with many sharing the same frequency, direction, and phase relationship. This coherence gives laser light its narrow beam, purity, and intensity. The fact that photons are bosons helps make that kind of shared state possible. An even more striking example is a Bose-Einstein condensate. When certain bosonic atoms are cooled to temperatures extremely close to absolute zero, many of them can settle into the same quantum state. Instead of behaving like a crowd of separate particles, they begin to act more like one large quantum object. This was predicted by Satyendra Nath Bose and Albert Einstein, and first created in dilute atomic gases in the 1990s. It is one of the rare cases where quantum behavior becomes visible across a larger scale, as if the tiny rules of particles have risen gently to the surface. The contrast is almost poetic. Fermions resist sameness, bosons embrace it. Fermions build layered structure because they cannot all occupy the same state. Bosons can gather together and produce coherent fields, force-carrying behavior, and collective quantum states. This does not mean every fermion is a lump of matter and every boson is a force in a simple cartoon sense. Physics is richer than that. But as a guiding idea, the distinction is powerful. Fermions help explain the architecture of atoms and materials. Bosons help explain how particles interact and how certain collective phenomena arise. This difference reaches from the smallest particles to the largest structures. In white dwarf stars, electron degeneracy pressure, rooted in the Pauli exclusion principle, helps support the star against gravitational collapse. In neutron stars, related quantum pressure involving neutrons becomes part of the extreme physics holding matter up under enormous gravity. Meanwhile, bosons such as photons carry starlight across space. Gluons bind quarks inside nuclear particles, and the weak force bosons participate in processes that help govern radioactive decay and nuclear reactions. The quiet distinction between fermions and bosons is written into stars, atoms, technology, and light. So the universe is not made from one kind of quantum ingredient behaving one way. It has particles that resist sharing, and particles that can gather together. It has fermions that help matter take shape, and bosons that help forces act and collective states emerge. This is one reason the world can have structure without becoming frozen, and interaction without dissolving into featureless confusion. The difference between fermions and bosons helps give reality both bones and breath. The stable architecture of matter and the flowing exchanges that let that matter move, shine, bind, change, and become the world around you. After particles, forces, and fields have entered the picture, the word empty begins to feel less simple than it once did. In everyday life, empty usually means there's nothing in the space that matters. An empty cup has no tea in it, which is tragic but understandable. An empty room contains no furniture. An empty road has no cars. The word suggests absence, quietness, and a kind of peaceful lack. Physics, being physics, looks at this ordinary word and gently ruins its simplicity. In quantum field theory, empty space is not treated as a plain blank nothing. It is understood as the lowest energy state of underlying fields. That phrase is important because it changes the question. Empty space is not necessarily space with all reality removed. It is space with no ordinary particles present. while the fields that can give rise to particles still exist. The electron field, the electromagnetic field, quark fields, and other quantum fields are not simply switched off, because a region contains no visible matter. They are part of the physical description of the universe itself. The vacuum, then, is not a box with absolutely nothing inside. It is more like the quietest possible condition of the fields. Quiet does not mean absent. A calm ocean is still an ocean. A silent piano is still capable of sound. These images are not exact, but they help soften the idea. The quantum vacuum is not full of ordinary objects, but it is not a philosophical nothingness either. It has structure. It has physical rules. It has measurable consequences. Even when all particles are removed from a region as far as possible, modern physics does not describe what remains as pure non-being. It describes a state of fields. Vacuum fluctuations are one of the most famous features of this strange emptiness. They describe restless variations in quantum fields, even in their lowest energy state. This is often pictured as particles and antiparticles constantly popping in and out of existence, like bubbles in a very intense invisible soup. That image is memorable, but it can also be misleading if taken too literally. The vacuum is not simply packed with tiny little particles appearing fully formed, checking their watches, and vanishing before anyone can ask questions. A more careful way to say it is that quantum fields have unavoidable fluctuations. Their values cannot be perfectly still in the classical sense, because quantum uncertainty applies even to fields. These fluctuations influence real calculations and measurable effects, but the popular image of virtual particles as ordinary particles briefly borrowing energy can make the vacuum sound more cartoonish than it is. Virtual particles are often best understood as useful features of the mathematics used to calculate interactions in quantum field theory. The restless vacuum is real in its consequences, but it should not be imagined too casually as empty space fizzing with tiny billiard balls. One of the clearest examples of the vacuum leaving a measurable trace is the Casimir effect. If two uncharged metal plates are placed extremely close together in a vacuum, they can experience a tiny attractive force. The idea is that the plates alter the allowed modes of quantum fields between them compared with the space outside. Only certain field patterns can fit between the plates, while more possibilities exist outside. This difference produces a small but measurable effect. The Casimir effect is fascinating because it suggests that changing the boundaries of empty space can change what the vacuum allows. Nothing obvious is pushing the plates together. There is no ordinary wind, no visible fluid, no tiny mechanical spring hiding between them. Yet the quantum fields respond to the geometry of the situation. The effect is extremely small, and measuring it carefully is technically demanding, but it has become one of the most famous examples of the vacuum behaving as something physically meaningful rather than as a simple absence. Empty space, once again, turns out to have opinions. Another subtle fingerprint of the quantum vacuum appears in the Lamb shift. In the hydrogen atom, quantum theory originally predicted certain energy levels to be exactly the same, but careful measurement showed a tiny difference between levels that were expected to match. This difference became known as the Lamb shift, after Willis Lamb, who measured it with Robert Rutherford in the 1940s. The explanation came from quantum electrodynamics, where interactions between the electron and fluctuations of the electromagnetic field slightly shift the atom's energy levels. This is a beautiful example of how the vacuum can reach into matter. Hydrogen is the simplest atom, with one proton and one electron, and yet even there, empty space is not completely passive. The electron does not exist in isolation from the quantum fields around it. The vacuum subtly affects its energy. The shift is tiny, but tiny does not mean unimportant. Precision physics often advances by noticing extremely small differences and then taking them seriously. The Lamb shift became important evidence for quantum electrodynamics, one of the most accurate scientific theories ever developed. The vacuum also matters because it changes how to think about nothingness itself. Absolute nothingness is a philosophical idea. No space, no time, no fields, no laws, no possibility of measurement, no anything at all. The quantum vacuum is not that. It is a physical state inside a physical theory. It has space-time. It has fields. It has mathematical structure. It can be affected by boundaries. It can influence atoms. It can participate in the behavior of particles and forces. Calling it nothing is convenient in ordinary speech, but scientifically, it is a very particular kind of something. This does not mean empty space is secretly crowded in the same way a room is crowded. The vacuum is not full of tiny furniture. It does not contain ordinary particles waiting around in darkness. It is emptiness in the physical sense of having no detectable real particles present, but it is not emptiness in the absolute sense. The distinction matters. Quantum physics has made nothingness more difficult because it has shown that even the least occupied physical state still belongs to a world of fields and laws, so the quantum vacuum is one of the quietest and strangest ideas in modern physics. It is not a mystical void, and it is not a simple blank. It is the lowest energy condition of fields that fill the universe. Its fluctuations must be handled carefully, without turning them into a cartoon swarm of temporary particles. Yet its effects are measurable, from the Casimir force between close plates to the Lamb shift in hydrogen. The emptier space physics can describe still has structure, still follows rules, and still leaves traces. Nothing, it turns out, is not always nothing. Sometimes it is the universe in its lowest whisper. The quantum vacuum already makes empty space feel less empty than expected, but tunneling makes boundaries feel less absolute. In everyday life, barriers are wonderfully straightforward. A hill must be climbed. A wall must be gone around, broken through, or politely avoided. If a ball does not have enough energy to roll over a hill, it rolls back down. Classical physics is very sensible about this. It has strong opinions about locked doors and insufficient effort. At quantum scales, barriers are still real, but they do not always behave like the rigid limits familiar from ordinary experience. A particle can sometimes be found on the other side of a barrier, even when classical physics says it does not have enough energy to cross. This is quantum tunneling. The name is vivid, although slightly misleading if imagined too literally. The particle is not digging a tiny tunnel with a tiny shovel, wearing a tiny hard hat, and asking for a tea break halfway through. Something subtler is happening. In classical physics, a particle approaching a barrier is treated rather like a small object approaching a hill. If it has enough energy, it can cross. If it does not, it cannot. The barrier is a hard limit. Quantum mechanics describes the situation differently. A particle is not represented only as a point with a definite path. It is described by a wave function, and that wave function gives the probability of finding the particle in different places. When the wave function meets a barrier, it does not usually stop with a perfectly sharp edge. It can extend into the barrier, and sometimes beyond it. That extension matters. If the barrier is thin enough, or the conditions are favourable enough, there can be a small probability of detecting the particle on the far side. The particle has not climbed over the barrier in the classical sense. It has not secretly gained the missing energy in some ordinary mechanical way. Instead, the quantum description allows a non-zero chance that the particle appears beyond a region where classical motion would have been forbidden. It is one of those moments where the universe does not break its rules. It simply reveals that its deeper rules were never the same as the simple ones humans first imagined. Tunneling occurs because quantum particles are described by wave functions that can extend into and beyond barriers. This is one of the most important points, because it keeps the idea grounded. Tunneling is not magic, and it is not a particle choosing to ignore reality because it is feeling adventurous. The probability depends on the shape and height of the barrier, the particle's energy, and the particle's mass. A thicker or higher barrier makes tunneling less likely. A lighter particle is generally more able to show tunneling than a heavier object. Scale matters enormously. This is why people do not normally tunnel through walls, no matter how confidently they walk toward them. In principle, the particles making up a person are quantum particles. In practice, a person is a vast, warm, complicated object interacting constantly with the environment. The probability of the whole person tunneling through a wall together is so unimaginably tiny that it is not a realistic event in the history of anything. The wall remains an excellent wall. Quantum tunneling is real, but it does not turn everyday life into a badly supervised ghost story. At tiny scales, though, tunneling can be extremely important. One of the most beautiful examples is nuclear fusion in stars. The sun shines because hydrogen nuclei combine through nuclear reactions that ultimately produce helium and release energy. But there is a problem. Atomic nuclei are positively charged, and positive charges repel each other. To fuse, nuclei must get close enough for the strong nuclear force to take over, but their electrical repulsion creates a barrier. Classical physics alone would suggest that, at the sun's core temperature, many nuclei should not have enough energy to overcome that barrier often enough to explain the sun's steady light. Quantum tunneling helps solve the problem. The nuclei do not always need to go over the full barrier in the classical sense. Because they have wave-like quantum behavior, there is a small chance that they can tunnel through the repulsive barrier and get close enough for fusion to occur. Each individual tunneling event may be unlikely, but the sun contains an enormous number of particles moving and colliding in its core. Across that vast crowd, rare events happen constantly. The result is the sunlight that warms Earth, feeds photosynthesis, drives weather, and makes a patch of morning light on the floor look far more ordinary than it really is. Tunneling also appears in radioactive decay. In alpha decay, an atomic nucleus emits an alpha particle, which is made of 2 protons and 2 neutrons. Inside the nucleus, the alpha particle can be trapped by a potential barrier. Classically, it may not have enough energy to escape. Quantum mechanically, there's a probability that it can tunnel through the barrier and emerge from the nucleus. This helps explain why radioactive decay can happen at all, and why different isotopes have different decay rates. The barrier shape and the tunneling probability matter deeply. This also connects to the probabilistic nature of quantum physics. A single unstable nucleus cannot usually be predicted to decay at one exact moment, but a large collection of identical nuclei follows a reliable statistical pattern, described by a half-life. That half-life is not a schedule taped to each atom, it is a probability rule for the group. Tunneling provides the mechanism for certain kinds of decay, and probability describes when those events occur across many atoms. Again, the individual event is uncertain, while the overall pattern can be measured with remarkable precision. One of the most practical uses of tunneling is the scanning tunneling microscope. This instrument can image surfaces at atomic scales by bringing an extremely sharp conducting tip very close to a surface. If a voltage is applied, electrons can tunnel between the tip and the surface, creating a tiny current. That tunneling current depends very sensitively on the distance between the tip and the atoms below it. Even a small change in separation can noticeably change the current. By scanning the tip across the surface and measuring how the tunneling current changes, scientists can build an image of the surface with extraordinary resolution. This does not mean the microscope takes an ordinary photograph of atoms, as if they were tiny beads posing politely for a portrait. It maps the electronic structure of the surface through tunneling behavior. Still, the result is astonishing. A quantum effect that sounds like pure strangeness becomes a tool for studying matter atom by atom. It turns the invisible rules of wave functions into something scientists can use with exquisite control. Tunneling also plays a role in electronic devices. Tunnel diodes, certain memory technologies, and some nanoscale components depend on the ability of electrons to pass through barriers in ways that classical physics would not allow. As devices become smaller, quantum effects become harder to ignore. What once seemed like a strange exception becomes part of engineering. The smaller the technology gets, the more it has to negotiate with the quantum world. At some scales, tunneling can be useful. At others, it can become a problem, allowing current to leak where engineers would prefer it not to go. Quantum physics is helpful, but not always obedient. The important thing is that tunneling does not mean particles cheat reality. It means reality's rules at small scales are different from the rules suggested by everyday walls, hills, and fences. Classical barriers are often treated as absolute if there is not enough energy to cross them. Quantum barriers are regions where the wave function may shrink dramatically, but not always vanish completely. If some of the wave function reaches the other side, there is a chance the particle can be found there. So tunneling is one of the clearest examples of quantum physics producing real effects in nature and technology. It helps stars shine, contributes to radioactive decay, allows microscopes to image surfaces atom by atom, and influences the design of tiny electronic devices. It is strange, but it is not lawless. It follows precise mathematical rules. The barrier is real. The particle is real. The probability is real. What changes is the old assumption that forbidden path must always remain completely forbidden. At quantum scales, nature sometimes leaves a faint possibility on the far side of the wall, and in a universe with enough particles, enough time, and enough stars, those faint possibilities can light the sky. Tunneling shows that quantum physics can reach through barriers that look impossible from a classical point of view. Chemistry shows something just as remarkable, but much closer to ordinary life. Quantum rules do not only appear in rare laboratory setups or inside stars, they are also behind the way atoms join, the way molecules hold their shapes, the way materials become solid, and the way colour appears in the world around you. Every quiet object nearby is, in its own very unshowy way, a quantum arrangement. Chemistry can feel like a separate subject from quantum physics, because it has its own language of reactions, bonds, acids, metals, salts, proteins, crystals, and many other useful things that do not sound like wave functions at bedtime. But underneath those chemical patterns are electrons occupying quantum states. Atoms bond because their electrons can settle into arrangements that are stable, shared, transferred, or rearranged. A molecule is not held together by tiny hooks and clasps. It is held together by electromagnetic attraction shaped by quantum rules. Chemical bonds form because electrons occupy quantum states around atoms and molecules. In a simple picture, atoms may share electrons, transfer electrons, or attract each other because of charge differences. But the deeper reason these arrangements have particular strengths, lengths, and directions comes from quantum mechanics. Electrons are not little beads clicking into place between atoms. They are described by wave-like states spread through regions of space. When atoms approach one another, their electron states can combine into molecular orbitals, creating arrangements where the total energy is lower than it would be if the atoms stayed apart. That lowering of energy is one of the great quiet incentives of chemistry. Systems tend to settle into stable arrangements when allowed. A hydrogen molecule forms when two hydrogen atoms share electrons in a way that creates a more stable state than two isolated atoms. The electrons are attracted to both positively charged nuclei, and the quantum arrangement helps hold the two atoms together. This does not mean molecules are static little sculptures. They vibrate, rotate, bend and interact. But the reason they remain molecules at all is that quantum electron states allow stable bonds to exist. The shapes of orbitals help determine how atoms bond. This is one of the places where quantum physics becomes geometry. Electron orbitals have different spatial patterns, and those patterns influence how atoms can overlap and share electron density. Some orbitals are roughly spherical. Others have two-lobed or more complex shapes. When atoms combine, their orbitals can overlap in different ways, creating bonds with particular directions and strengths. This is why molecules have shapes, not just ingredients. Water is bent, carbon dioxide is linear, methane forms a roughly tetrahedral shape. These forms are not random decorations, they come from electron arrangements. Molecular geometry matters enormously. The shape of a molecule affects how it reacts, how it dissolves, how it absorbs light, how it fits into biological structures, and how it behaves in materials. A molecule is not just a list of atoms, it is a three-dimensional quantum arrangement. The difference between one molecular shape and another can be the difference between a harmless substance and a poisonous one, a pleasant smell and an unpleasant one, a flexible material and a rigid one. Chemistry is architecture at the scale of atoms, and quantum mechanics supplies many of the building rules. The periodic table is also a quantum pattern hiding in plain sight. It may look like a chart of element names, numbers, and boxes, but its deeper structure comes from electron shells and subshells. Electrons in atoms occupy allowed states, and those states are filled in a particular order, shaped by energy, spin, and the Pauli exclusion principle. As electrons fill shells around the nucleus, chemical behavior begins to repeat in regular ways. This repetition is why elements in the same column often share similar properties. The noble gases, for example, are generally unreactive because their outer electron shells are already filled in a stable way. The alkali metals are highly reactive because they have one outer electron that can be given up relatively easily. The halogens often seek one more electron to complete an outer shell. These patterns are not just chemical trivia, they are quantum structure made visible as a table. Dmitri Mendeleev arranged the periodic table before the full quantum explanation existed, but quantum mechanics later revealed why the pattern works so deeply. The table is not simply a human filing cabinet for elements, it is a map of electron behavior. Color, too, often comes from quantum transitions. When electrons absorb energy, they can move from one allowed state to another. When they fall back to a lower energy state, they may emit light. Because only certain energy differences are allowed, atoms and molecules absorb or emit specific wavelengths. Those wavelengths correspond to colors or to forms of light outside the visible range. This is why atomic spectra appear as distinctive lines rather than a continuous smear. The light carries information about the quantum structure of the matter that produced it. In materials, color can arise in several quantum ways. Pigments absorb some wavelengths of visible light and reflect others because of the energy levels available to their electrons. The green of chlorophyll, the red of many compounds, the blue of certain minerals, and the glow of neon signs all involve electrons interacting with light in energy-specific ways. Even when color involves more complex effects such as crystal fields, band structures, or structural color, quantum physics is still nearby, shaping how matter deals with electromagnetic radiation. Solids also depend on quantum rules. In a metal, electrons can move through a lattice of atoms in ways described by quantum band structure. In an insulator, the available energy bands make it difficult for electrons to move freely. In a semiconductor, the gap between energy bands is just right for controlled electrical behavior, which is why semiconductors can become the foundation of computers, phones, sensors, and solar cells. These everyday technologies are not merely clever engineering, they are applied quantum chemistry and quantum physics in carefully arranged materials. Even the fact that matter has texture and durability depends on electron behavior. Glass, plastic, wood, ceramic, metal, water, salt, and skin all feel different because their atoms and molecules are bonded and arranged differently. Some bonds are strong and directional, some interactions are weaker and more flexible. Some structures form crystals, others form tangled polymers or disordered networks. The world's material variety is not produced by atoms alone, but by the quantum rules governing how atoms can combine. This is why quantum physics is not hidden only in laboratories, behind lasers, vacuum chambers, and machines with alarming warning stickers. It is in the chemistry of breathing, the colour of a screen, the hardness of a mug, the softness of fabric, the smell of rain on dry ground, the taste of salt, and the proteins quietly folding inside living cells. It is present whenever atoms share electrons, whenever molecules take shape, whenever light is absorbed, and whenever matter holds itself together well enough to become familiar. Chemistry is the ordinary face of quantum physics. It is what happens when the strange rules of electrons, orbitals, energy levels, spin, and exclusion become rich enough to build substances. Quantum mechanics does not make the world less solid or less real. It explains why the world can be solid, colourful, reactive, stable, flexible, transparent, fragrant, poisonous, nutritious, metallic, soft, brittle, or alive. The deep rules are strange, but their results are beautifully ordinary. Around the listener right now, in every surface and shadow, quantum physics is not making a spectacle of itself. It is simply holding matter together. Chemistry shows how quantum rules can quietly build the familiar world, but sometimes those rules become visible in a more dramatic way. Usually quantum behavior is hidden beneath the warmth, motion, and messiness of everyday conditions. A table does not show an interference pattern. A cup of tea does not behave like one giant wave, although after a long day it may feel emotionally important enough to try. Most large objects interact with their surroundings so constantly that delicate quantum effects are washed out almost immediately. But under special conditions, especially very low temperatures, quantum behavior can rise from the invisible scale of particles into the human-sized world, not always in a way that can be seen with the naked eye directly, but in effects large enough to measure, demonstrate, and sometimes even watch. Superconductors, superfluids, and Bose-Einstein condensates show that quantum physics is not trapped forever inside atoms. When enough particles act together in a coordinated quantum state, the small rules can become large enough to surprise the senses. Superconductors are among the most striking examples. A superconductor is a material that can conduct electric current with zero electrical resistance when it is cooled below a critical temperature. In an ordinary wire, electrical resistance causes some energy to be lost as heat. That is why wires can warm up when current passes through them. Electrons moving through the material scatter from atoms, impurities, and vibrations in the lattice. The flow is useful, but it is not perfect. Some energy is always being wasted along the way. In a superconductor below the right temperature, the electrons no longer behave like a normal crowd of independent charged particles. They enter a collective quantum state. In many conventional superconductors, electrons form paired states known as Cooper pairs, named after Leon Cooper. These pairs behave differently from individual electrons and can move through the material in a coordinated way without ordinary resistance. This does not mean the electrons have become magically frictionless marbles. It means the material's quantum state has changed. The rules governing the whole system now allow current to persist without the usual energy loss. This effect is not just a laboratory curiosity. Superconductivity is used in powerful magnets, especially in medical imaging machines, particle accelerators, and scientific instruments. Superconducting magnets can carry very large currents without wasting huge amounts of energy as heat, although keeping them cold can itself be a serious engineering challenge. The dream of superconductors that work easily at room temperature remains one of the great goals in materials science. Such a discovery could change power transmission, transport, electronics, and many other technologies. For now, superconductivity remains a reminder that matter can enter states that seem almost impossible from the viewpoint of ordinary warm materials. Another strange feature of superconductors is the Meissner effect. When a material becomes superconducting, it can expel magnetic fields from its interior. This is not simply the same as being a perfect conductor. It is a separate quantum behavior discovered by Walter Meissner and Robert Oxenfeld in the 1930s. The superconductor reorganizes itself so that magnetic fields are pushed out, except in certain special cases and under certain limits. The result can look beautifully strange. The Meissner effect is responsible for some demonstrations of magnetic levitation. A magnet can hover above a cooled superconductor because the superconductor responds by excluding magnetic fields, creating forces that can support the magnet. Under the right conditions, the magnet may appear to float, locked in a stable position above the surface. It is one of those demonstrations that looks like a magic trick, except the trick is that the universe is doing advanced quantum materials physics, while everyone else is politely staring. This levitation is not caused by anti-gravity, and it is not a loophole in the laws of nature. It comes from electromagnetic forces shaped by a collective quantum state. The superconductor is not behaving like an ordinary metal. Its electrons have entered a coordinated state that changes how the material responds to magnetic fields. What makes the demonstration so powerful is that a quantum effect, usually associated with invisible particles, becomes large enough to see across a tabletop. The effect is still delicate. It depends on temperature, material type, magnetic field strength, and other conditions. But it shows that quantum physics can become almost theatrical when the circumstances are right. Superfluid helium offers another extraordinary example. Helium can become a superfluid when cooled to extremely low temperatures. In this state, it can flow with almost no viscosity. Viscosity is a fluid's internal resistance to flow. Honey has high viscosity. Water has much lower viscosity. Superfluid helium behaves in a way that makes even water look rather sluggish and conventional. It can flow through tiny openings, creep along surfaces, and behave in ways that seem deeply unintuitive from the standpoint of ordinary liquids. The reason is that superfluid helium is not just cold helium moving normally. It is a collective quantum state involving many helium atoms. The atoms are acting together in a coordinated way, and that coordination gives the liquid unusual properties. Superfluidity shows that quantum mechanics is not only about isolated particles. Under the right conditions, a visible amount of matter can behave according to a shared quantum order. A liquid becomes something stranger than a liquid in the everyday sense, while still being entirely real and measurable. This is one of the reasons low-temperature physics is so fascinating. Cooling a system removes much of the random thermal motion that normally disrupts delicate quantum behavior. Warmth is wonderful for blankets, soup, and general morale, but it is often terrible for preserving quantum coherence. At extremely low temperatures, particles can settle into organized quantum states that would be overwhelmed at room temperature. The hidden order becomes visible because the noise has been quieted. Nature's smallest rules are still there at ordinary temperatures, but they are usually buried under thermal bustle. Bose-Einstein condensates take this idea even further. A Bose-Einstein condensate occurs when many bosons occupy the same quantum state, causing them to behave almost like one giant matter wave. The idea was predicted by Satyendranath Bose and Albert Einstein in the 1920s, but it was first created in dilute gases of atoms in the 1990s. To make one, scientists cool atoms to temperatures incredibly close to absolute zero, where ordinary thermal motion nearly disappears. In that extreme cold, the atom's wavelengths become large enough to overlap. Instead of behaving as separate little particles, many atoms fall into the same quantum state. The result is a new state of matter, one that reveals quantum behavior across a much larger scale than usual. It is sometimes described as a giant matter wave, though again, the phrase should be treated carefully. The atoms do not become a single ordinary object. They share one coherent quantum state, allowing scientists to study quantum behavior in a controlled and remarkable way. Bose-Einstein condensates are valuable because they give researchers a kind of magnified quantum system. They can be used to study interference, superfluidity, quantum vortices, precision measurement, and the behavior of matter under unusual conditions. They are fragile and require extremely careful laboratory control, but their existence is profound. They show that the rules governing individual particles can, under the right circumstances, organize whole clouds of atoms into one shared quantum pattern. These large-scale quantum effects all share a common lesson. Quantum physics usually hides because the everyday world is warm, noisy, and constantly interacting with itself. Particles bump, scatter, vibrate, radiate, and exchange energy with their surroundings. Those interactions destroy the delicate relationships needed for obvious quantum behavior. But remove enough thermal noise, isolate the system carefully enough, and allow particles to enter a shared state, and the hidden rules can rise into view. Superconductors, superfluids, and Bose-Einstein condensates do not make quantum physics less strange. They make it harder to dismiss as something that only happens in invisible corners of reality. A current can flow without resistance. A magnet can hover above a cold material. A liquid can move with almost no viscosity. A cloud of atoms can act like one coherent matter wave. These are not metaphors. They're physical phenomena measured and studied in laboratories. So quantum rules are not always confined to the tiny. Most of the time, they are buried beneath warmth and disorder, quietly building the ordinary world without drawing attention to themselves. But under special conditions, the delicate mathematics of quantum states can become large enough to shape visible matter. The small world does not stay small because it is weak. It stays hidden because ordinary life is noisy. When the noise is lowered, the deeper music can sometimes be heard. Once quantum rules have appeared in superconductors, superfluids, and other unusual states of matter, it becomes easier to see that quantum physics is not sealed away in abstract theory. It is not only something that happens inside particle accelerators, deep space equations, or carefully chilled laboratories with machines that look as if they require both a manual and a small act of courage. Quantum physics is also inside the tools of ordinary modern life. Most people do not wake up, check their phone, turn on a light, use a computer, follow satellite navigation and think, "Ah yes, a refreshing morning of applied quantum mechanics." But that is exactly what is happening in the background. The modern world is full of devices that depend on electrons moving through materials in ways that only make sense because of quantum theory. The strangeness is still there. It has simply been engineered into something useful, reliable, and small enough to fit in a pocket, where it can immediately distract someone from the thing they were supposed to be doing. Transistors are among the most important examples. A transistor is a tiny electronic switch or amplifier, and modern computers contain huge numbers of them. They are made from semiconductors, materials whose electrical behavior sits between conductors and insulators. Silicon is the most famous example. What makes semiconductors so useful is not just that they can carry electricity sometimes, and resist it at other times. It is that their behavior can be carefully controlled by their quantum band structure. In a solid, the allowed energy levels of electrons spread into bands. Some bands are filled, some are empty, and the gap between them determines whether electrons can move easily through the material. Metals conduct because electrons have available states they can move into. Insulators resist current because their electrons cannot easily jump across a large energy gap. Semiconductors have a smaller gap, which can be manipulated by adding tiny amounts of other elements, applying voltages, or shining light. This gives engineers control over electron flow. That control is what makes transistors possible. A transistor can act like a switch, turning current on or off, or like an amplifier, controlling a larger signal with a smaller one. Billions of these switches work together inside processors and memory chips. Their behavior is described through solid-state physics, which is deeply quantum. Without energy bands, electron states, the Pauli exclusion principle, and the quantum behavior of materials, the digital world would not have its present form. The internet, laptops, cameras, phones, and games that somehow need an update exactly when someone wants to relax all depend on these tiny quantum-controlled switches. Lasers are another everyday quantum technology, even though they still manage to sound futuristic. The word laser comes from light amplification by stimulated emission of radiation. The key idea is stimulated emission. Atoms, molecules, or semiconductor materials can be placed into excited states, meaning their electrons have been given extra energy. When the right photon passes by, it can stimulate an excited atom or material to emit another photon with the same energy, direction, and phase. The result is highly organized light. Ordinary light is often messy. A lamp sends photons in many directions, with many phases and sometimes many wavelengths. Laser light is much more coherent. Its photons can be tightly coordinated, which allows a laser beam to stay narrow, focused, and precise. This is why lasers can scan barcodes, carry information through optical fibers, read discs, perform delicate surgery, measure distances, and create little red dots that make cats briefly reconsider the nature of hunting. The laser is a perfect example of quantum physics becoming practical. It depends on discrete energy levels, photon emission, and the ability of matter to interact with light in specific quantum ways. When the first lasers were developed in the 20th century, they were sometimes described as a solution looking for a problem. That problem was soon solved by finding many problems. Lasers are now everywhere, quietly using one of the strangest features of atomic physics to do extremely normal jobs. Light-emitting diodes, often called LEDs, also depend on quantum behavior in semiconductors. An LED produces light when electrons move through a semiconductor and lose energy by emitting photons. The color of that light depends on the energy gap in the material. A larger gap produces higher energy light. A smaller gap produces lower energy light. By choosing and designing different semiconductor materials, engineers can create LEDs that emit different colors, from red and green to blue and white. This might sound like a simple light source, but it is a triumph of quantum materials engineering. The glow from an LED is not caused by heating a filament until it shines, as in an old incandescent bulb. It is produced by electrons and holes recombining across an energy gap and releasing energy as light. Because the process can be very efficient, LEDs use less energy and last longer than many older lighting technologies. The little indicator lights on electronics, the bright lamps in homes, the displays in screens, and many modern streetlights all depend on carefully controlled quantum transitions. Atomic clocks show quantum precision in a different way. A mechanical clock keeps time through moving parts, such as a pendulum or a spring. A quartz clock uses the regular vibration of a quartz crystal. An atomic clock goes deeper, using the extremely consistent frequency of quantum transitions in atoms. Atoms can absorb or emit radiation at very specific frequencies when their electrons or internal states change. These frequencies are far more stable than most human-made mechanical rhythms. Cesium atomic clocks have been especially important in defining the second. The modern definition of the second is based on a particular transition in cesium atoms. This is not because cesium has a charming personality, although it is doing its best. It is because identical atoms of the same element behave with astonishing consistency. A cesium atom in the right conditions is the same kind of cesium atom anywhere. Its quantum transition provides a universal timing reference. Atomic clocks matter far beyond scientific laboratories. Satellite navigation systems depend on extremely precise timing. Signals travelling from satellites to receivers on Earth must be timed with great accuracy, because even tiny timing errors can turn into large position errors. Telecommunications, financial systems, electrical grids, and scientific measurements also depend on precise timekeeping. The modern world is synchronized by quantum transitions so steady that they make ordinary clocks look charmingly wobbly. This is one of the quieter surprises of quantum physics. The same theory that says particles can behave like waves in empty space is not completely empty, also allows civilization to coordinate itself with extraordinary precision. It helps computers process information, lasers carry signals, LEDs light rooms and screens, and atomic clocks keep global systems aligned. The theory may sound abstract, but its fingerprints are all over the ordinary day. Quantum physics is not just a strange story about tiny things behaving badly under experimental supervision. It is part of the machinery holding modern life together. It lives in the materials inside phones, the light from screens, the timing of satellites, the sensors in laboratories, the lasers in medicine, and the electronics woven through homes, cities, vehicles, and communication networks. The modern world does not merely use quantum physics in a few special places, it is built on it, and perhaps that makes the strangeness feel a little different. Quantum physics is not distant because it is small. It is only hidden because the technology works so smoothly that the weirdness disappears behind convenience. A phone lights up, a message sends, a clock stays accurate, a scanner reads, a laser measures. Beneath each ordinary action, electrons occupy bands, photons are emitted, atoms transition, and fields obey rules that once seemed almost impossible. The world feels familiar at the surface, but much of its modern machinery is powered by the quiet precision of the quantum world below. The quantum machinery of the modern world does not stop at phones, clocks, lasers, and screens. It also reaches into the human body, not as something mystical or separate from biology, but as part of the physical rules that make life measurable. The body is warm, wet, restless, and complicated, which is not usually the easiest place to preserve delicate quantum behaviour. Living tissue is not a silent vacuum chamber. It is more like a busy city made of water, ions, proteins, membranes, electrical signals, chemical reactions, and cells, constantly doing very small jobs with impressive commitment. And yet, quantum physics still matters deeply in how scientists study the body. Some of the most powerful ways of seeing inside living tissue depend on quantum properties of atoms, nuclei, molecules, and light. Medical imaging is not simply a matter of shining a torch through a person and hoping for the best, which would be both ineffective and socially difficult. It uses carefully controlled physics to turn invisible structures into useful information. Quantum rules help reveal organs, blood flow, tumours, brain activity, cellular chemistry, and the hidden patterns of life. MRI, or magnetic resonance imaging, depends on nuclear spin. In the body, one of the most useful nuclei for this purpose is hydrogen, because hydrogen is abundant in water and fat. Since the human body contains a great deal of water, it contains many hydrogen nuclei, each of which behaves like a tiny quantum system with spin. When a person is placed inside the strong magnetic field of an MRI scanner, many of these nuclear spins tend to align with or against the field in specific quantum ways. The scanner then uses carefully tuned radio waves to disturb that alignment. When the nuclei relax back toward their lower energy state, they emit signals that can be detected. Different tissues produce different signals because their hydrogen nuclei sit in different chemical and physical environments. Water-rich tissue, fat, muscle, blood, and damaged tissue can all respond in subtly different ways. A computer then reconstructs these signals into detailed images. The result can show soft tissues with remarkable clarity, making MRI especially useful for the brain, spine, joints, organs, and many other parts of the body. Beneath the image is nuclear spin, quietly turning quantum behavior into medical vision. Positron emission tomography, usually called PET, uses a different and more energetic quantum process. In a PET scan, a patient is given a radioactive tracer, often a molecule similar to glucose that has been labelled with a radioactive isotope. Cells that use more of the tracer can then be identified, which is useful because some tissues, including many cancers, consume energy differently from surrounding tissue. The radioactive isotope emits a positron, which is the antimatter counterpart of the electron. The positron does not usually travel far. Soon after it is emitted, it meets an electron in the surrounding tissue. When matter and antimatter meet in this way, they annihilate, converting their mass into energy. This produces gamma rays, usually emitted in opposite directions. Detectors around the patient register these gamma rays, and computers use the timing and direction of the signals to reconstruct where the tracer is concentrated inside the body. It sounds almost like science fiction, but it is practical medicine, antimatter being used to map biology. PET imaging can reveal metabolic activity rather than just structure, showing not only what the body looks like, but where certain processes are especially active. Fluorescence imaging also depends on quantum transitions, though it often feels gentler because it deals with light and molecules rather than antimatter. In fluorescence, a molecule absorbs light of one energy and then emits light at a lower energy. The absorbed light raises electrons in the molecule to a higher quantum state. After losing some energy through internal molecular motion or interactions, the molecule returns to a lower state and emits a photon. Because the emitted photon has less energy than the absorbed one, it usually has a longer wavelength and a different colour. This process lets scientists tag and track specific structures in cells and tissues. Fluorescent dyes and proteins can be attached to particular molecules, allowing researchers to see where those molecules are, how they move, and how cells are behaving. Green fluorescent protein, originally discovered in jellyfish, became one of the most important tools in biology because it allowed living cells to glow in ways that reveal internal processes. Fluorescence microscopy can show proteins moving through cells, neurons firing, immune cells responding, and tissues changing over time. It is quantum light behavior turned into a biological lantern. Photosynthesis brings quantum physics even closer to life's everyday machinery. Plants, algae, and some bacteria absorb light and use its energy to help build chemical fuel. At the heart of this process are molecules such as chlorophyll, which absorb photons. When a photon is absorbed, it raises an electron in the molecule to an excited state. That excitation energy must then move through molecular structures toward a reaction center, where it can help drive chemical changes. This is a quantum process because it involves discrete energy levels, photon absorption, electron excitation, and energy transfer between molecules. There has been significant scientific interest in whether quantum coherence plays a useful role in the movement of excitation energy during photosynthesis. Some experiments suggest that wave-like quantum behavior may appear briefly in certain photosynthetic complexes, but this should be handled carefully. A leaf is not a tidy quantum computer, and living systems are warm, noisy, chemically active environments. Any quantum coherence in photosynthesis must survive only briefly and within a highly structured molecular setting. The more grounded point is still fascinating enough. Photosynthesis depends on quantum events at the molecular level because light energy must be absorbed, transferred, and converted through the rules of electrons and photons. This matters because biology is sometimes imagined as separate from physics, as though living things float above the rules that govern the rest of matter. But life is not exempt from physics. It is physics arranged into chemistry, chemistry arranged into cells, and cells arranged into organisms that somehow remember to breathe, blink, heal, digest, sleep, and occasionally crave snacks at extremely inconvenient times. Quantum physics does not explain everything about biology by itself, but it helps explain the behavior of the molecules on which biology depends. The body is full of quantum processes, though most of them do not look like the dramatic examples from textbooks. Electrons occupy molecular orbitals. Chemical bonds form and break. Proteins absorb and emit energy. Pigments interact with light. Nuclei respond to magnetic fields. Radioactive traces decay. Photons carry information into detectors. At the scale of cells and tissues, these processes become part of larger biological systems, shaped by warmth, water, enzymes, membranes, and constant molecular motion. The quantum rules are still there, but they're woven into a much more complex fabric. Medical imaging and biological detection work because scientists have learned how to ask the body careful physical questions. MRI asks hydrogen nuclei how they respond to magnetic fields and radio waves. PET asks where radioactive traces are being used and detects the gamma rays released after positron annihilation. Fluorescence imaging asks molecules to glow in specific ways so their locations and movements can be followed. Photosynthesis shows how living systems capture photons and move energy through molecular structures. Each example turns a quantum property into a way of seeing, measuring, or sustaining life. So quantum physics is not separate from biology. It is not a cold little theory locked away from living things. It quietly helps scientists image the brain, detect disease, follow molecules inside cells, understand how light becomes chemical energy, and measure processes that would otherwise remain hidden. The body may feel warm, familiar, and beautifully ordinary from the inside, but it is still made from atoms, molecules, photons, nuclei, and electrons. Beneath every heartbeat and breath, the quantum world is not making life less alive. It is helping make life visible. Quantum physics helps reveal the body through medical imaging and biology, but it also does something even more unusual. It turns possibility itself into a resource. In ordinary computing, information is built from bits, and each bit is treated as either 0 or 1. That simple difference, repeated billions and billions of times, allows computers to store images, play music, run websites, send messages, and occasionally freeze at the exact moment someone has not saved their work. The ordinary bit is wonderfully useful because it is definite. Quantum computing begins with something less definite. Its basic unit of information is called a qubit. A qubit can be represented by physical systems such as the spin of a particle, the energy state of an atom, the polarization of a photon, or current states in a superconducting circuit. What makes it quantum is that it can be placed in a superposition of possible states. Instead of being only 0 or only 1 in the ordinary sense, a qubit can be described as a combination of both possibilities before measurement. This does not mean a qubit is magically doing every calculation at once in the simple way often suggested. It means its state carries quantum amplitudes, and those amplitudes can be manipulated according to quantum rules. The true power of quantum computing is not that it tries every answer, like an overexcited librarian flinging open every drawer at the same time. That popular image is catchy, but misleading. Quantum computers use interference. Their calculations are designed so that wrong or unwanted possibilities tend to cancel out, while useful possibilities become more likely to appear when the final measurement is made. This is delicate. It requires the quantum state to evolve in a controlled way, preserving phase relationships so that amplitudes can combine properly. Interference is why quantum algorithms are so different from ordinary algorithms. A classical computer follows definite logical steps using bits. A quantum computer prepares qubits, applies quantum operations, and arranges the evolution of the system so the final probabilities are shaped toward a desired result. The answer is still obtained through measurement, and measurement produces a definite outcome. The cleverness lies in how the possibilities are guided before that moment. Quantum computing is less like opening every door at once, and more like setting up a very precise pattern of waves so that the wrong ripples fade and the right ones rise. Entanglement also plays a central role. When qubits become entangled, their states cannot always be described separately. The whole system carries relationships that are not reducible to each qubit alone. These correlations are central to many quantum algorithms and quantum information protocols. Entanglement can allow quantum systems to process information in ways that have no ordinary classical equivalent. It is not a magic ingredient by itself, and not every entangled system automatically becomes useful. But in carefully designed quantum circuits, entanglement helps create the complex structure that quantum algorithms need. This is one reason quantum computers are so difficult to build. A useful quantum processor must keep qubits isolated enough to preserve fragile quantum relationships, while still allowing them to be controlled, connected, and measured. That is a slightly unfair engineering challenge, rather like asking someone to keep a soap bubble perfectly intact while also writing instructions on it, passing it around a room, and expecting it to perform mathematics. Qubits are sensitive to noise, heat, stray electromagnetic fields, imperfect controls, and unwanted interactions with the environment. Those disturbances can cause decoherence, which destroys the delicate phase relationships needed for quantum computation. Quantum error correction is therefore essential. Ordinary computers also use error correction, but quantum error correction is much harder because quantum information cannot simply be copied. The no-cloning theorem says an unknown quantum state cannot be perfectly duplicated. So instead of making straightforward backups, quantum error correction spreads information across many physical qubits in a carefully encoded way. The aim is to detect and correct errors without directly measuring and destroying the quantum information being protected. This is one of the major barriers between today's experimental quantum machines and large fault-tolerant quantum computers. A single, logical qubit, one protected unit of usable quantum information, may require many physical qubits working together. The more complex the calculation, the more protection is needed. This does not make quantum computing impossible, but it does make it far more difficult than the glossy version sometimes suggests. Quantum computers are promising, but they are not simply faster versions of laptops. They are specialized machines that may offer major advantages for particular kinds of problems, such as simulating quantum systems, improving certain optimization methods, and breaking or reshaping some forms of cryptography. So quantum computing uses possibility as a tool, but not as a shortcut around reality. A qubit can hold a superposition. Interference can shape probabilities. Entanglement can build correlations across a larger quantum state. Error correction can protect fragile information from noise. The goal is not to make a mystical computer that knows everything. The goal is to build machines that use the real mathematical structure of quantum physics to solve certain problems in ways classical computers cannot easily match. It is one of the clearest signs that the strangeness of the small world is not only something to interpret, it is something that can be engineered. From quantum information, the scale can widen almost absurdly. The same theory that describes qubits, atoms, and particles also reaches into stars, stellar remnants, black holes, and the early universe. Quantum physics is often described as the science of the very small, and that is true in one sense. But the very small does not stay politely small. Tiny rules can shape enormous objects. The behavior of particles can decide how stars shine, how dead stars resist collapse, and how the early universe may have planted the seeds of galaxies. The sun shines because nuclear fusion turns hydrogen into helium in its core. Deep inside the sun, hydrogen nuclei are squeezed together under immense pressure and temperature. But even there, they face a problem. Hydrogen nuclei are positively charged, and positive charges repel each other. To fuse, they must get close enough for the strong nuclear force to take over, binding them into heavier nuclei. Classical physics alone would make this process far less efficient at the sun's core temperature. Quantum tunneling helps make fusion possible. Because nuclei have wave-like quantum behavior, there is a small probability that they can tunnel through the electrical repulsion barrier instead of needing to climb fully over it in the classical sense. Each individual fusion event is unlikely, but the sun contains a vast number of particles colliding constantly in its core. Across that enormous crowd, rare quantum events become steady power. The sunlight falling on Earth, warming oceans, driving weather, feeding plants, and lighting a quiet room began partly with tunneling. A tiny quantum possibility becomes a star's long golden patience. Quantum physics also helps explain white dwarf stars. A white dwarf is the dense remnant left behind after a star like the Sun has exhausted its nuclear fuel and shed its outer layers. Without ongoing fusion to support it, gravity tries to compress the remaining core. But the star does not simply collapse without limit. It is supported by electron degeneracy pressure, which comes from the Pauli exclusion principle. Identical electrons cannot all occupy the same quantum state, so as matter is squeezed more tightly, electrons resist being forced into identical arrangements. This resistance is not heat pressure in the ordinary sense. It does not depend on the star being hot in the same simple way that gas pressure does. It is quantum pressure arising from the allowed states available to electrons. In a white dwarf, the mass of a star can be packed into an object roughly the size of Earth, supported not by combustion or ordinary chemical structure, but by a deep rule about fermions. The Pauli exclusion principle, which helps explain the periodic table and chemistry, also helps hold up a dead star. That is quite a career for one principle. Neutron stars take the story even further. When a massive star explodes in a supernova, its core can collapse into an object far denser than a white dwarf. Protons and electrons are crushed together into neutrons, and the remaining object becomes a neutron star. These stars are only about the size of a city, yet they can contain more mass than the Sun. Their matter is compressed beyond anything found in ordinary atoms. A teaspoon of neutron star material would have an almost unimaginable mass, though removing a teaspoon is not recommended and would require a level of cutlery engineering not currently available. Neutron stars are shaped by extreme quantum physics, nuclear forces, and degeneracy pressure involving neutrons. the physics inside them is still an active area of research because their densities are so extreme that ordinary matter models are stretched to their limits. They may contain exotic states of matter, superfluid components, superconducting regions, and behavior governed by the strong nuclear force under crushing conditions. These are not merely large balls of neutrons sitting quietly in space. They are laboratories created by gravity, where quantum rules and nuclear physics are forced into their most intense forms. Black holes bring quantum physics into an even stranger relationship with space and gravity. According to general relativity, a black hole has an event horizon, a boundary beyond which nothing can escape once it has crossed inward. Classically, a black hole is black because no light can get out. But in the 1970s, Stephen Hawking combined ideas from quantum field theory with curved space-time and found that black holes should not be completely black. They should emit a faint form of radiation, now called Hawking radiation. The basic idea is that quantum fields near an event horizon behave differently from fields in ordinary flat space. The presence of the horizon changes how particles and radiation are defined for distant observers. The result is that a black hole can slowly lose energy over time. For large astrophysical black holes, this radiation is incredibly faint, far colder than the cosmic microwave background, and impossible to detect with current practical methods. But the idea is profound. It suggests that black holes have temperature, entropy, and a connection to quantum information. Hawking radiation also points toward one of the deepest unsolved problems in physics: how to unite quantum mechanics with gravity. Quantum field theory works beautifully for particles and forces in many settings. General relativity works beautifully for gravity, space-time, planets, stars, galaxies, and black holes. But at the event horizon, and especially near the singularity, the two great theories begin to press against each other. Black holes become places where the unfinished parts of physics are impossible to ignore. So quantum physics is not only the science of tiny laboratory systems, it reaches outward. It helps explain why the sun burns steadily instead of failing to fuse. It helps explain why white dwarfs resist collapse through electron degeneracy pressure. It helps shape neutron stars, where matter is crushed into one of the densest forms known in the universe. It even suggests that black holes may slowly radiate, meaning the darkest objects in the cosmos are not perfectly dark after all. The small rules echo at enormous scales. Tunneling light stars. The Pauli exclusion principle supports stellar corpses. Quantum fields whisper at the edges of black holes. This same theory that makes electrons behave strangely in a laboratory also helps explain some of the brightest, densest, and most mysterious objects in space. Quantum physics begins beneath the surface of matter, but it does not stay there. Given enough gravity, enough heat, enough density, or enough cosmic time, the smallest rules can become written across the sky. After quantum physics has reached through technology, biology, stars, and black holes, the question becomes quieter and more difficult. The theory works. It predicts experiments with extraordinary accuracy. It explains atoms, chemistry, light, particles, materials, and many of the technologies woven through modern life. But once the calculations are done and the results match, a deeper question remains waiting in the dim background. What is quantum physics actually saying about reality? This is where interpretations enter. An interpretation of quantum mechanics is not usually a different set of experimental predictions. It is a different way of understanding what the mathematics means. The equations may be the same, the laboratory results may be the same, but the story told about what is happening beneath those results can change dramatically. Quantum physics is unusual because its practical success is astonishingly clear, while its deeper meaning remains unsettled. It is a little like having a map that gets every road correct, while still leaving people arguing about what the landscape is made of. The Copenhagen interpretation is one of the oldest and most influential ways of thinking about quantum mechanics. It's associated with Niels Bohr and Werner Heisenberg, though the phrase covers a family of related views rather than one perfectly tidy doctrine. Broadly, it emphasizes measurement outcomes and the practical rules for using quantum mechanics. Instead of trying to give a simple picture of what a quantum system is doing before measurement, it focuses on what can be predicted, measured, and communicated through experiments. In this view, the wave function is often treated as a tool for calculating the probabilities of possible measurement results. Before measurement, the theory gives a range of possible outcomes. During measurement, one result is obtained. Copenhagen-style thinking tends to be cautious about asking for a familiar hidden picture underneath, because the quantum world does not seem to behave like a collection of little classical objects carrying definite properties at all times. This can feel unsatisfying, because the human mind enjoys being told what is really going on behind the curtain. Copenhagen often replies, quite firmly, that physics should describe what can be observed and predicted, not necessarily provide a cozy mechanical cartoon. The many worlds interpretation takes a very different route. Proposed by Hugh Everett in the 1950s, it treats the wave function as something that always evolves smoothly, according to the quantum equations. In this view, there is no special collapse of the wave function when measurement happens. Instead, when a quantum event has several possible outcomes, all outcomes continue in different branches of reality. The observer becomes part of the branching structure. Each version experiences one definite result, while the full wave function contains them all. This idea can sound wildly extravagant, because it suggests an enormous, perhaps endlessly branching reality. Every quantum measurement does not simply choose one outcome while the others vanish. Instead, the alternatives persist in separate branches that no longer interact in ordinary ways. It is an unsettling thought, and not exactly something to bring up casually when someone only asked whether the kettle had boiled. But many worlds has an appeal for some physicists, because it removes the special mystery of wave function collapse. The mathematics keeps evolving. The strangeness shifts from sudden measurement collapse to the existence of many non-communicating branches. Pilot wave theory offers another possibility. It is often associated with Louis de Broglie and later David Bohm. In this interpretation, particles have definite positions, but they are guided by a real wave. The particle follows a clear path, while the guiding wave evolves according to quantum rules and influences where the particle goes. This gives a more definite picture than many other interpretations. There is always an actual particle somewhere, not merely a set of possible outcomes waiting for measurement. But pilot wave theory comes with its own unusual features. To reproduce the predictions of quantum mechanics, the guiding wave must behave in a way that is deeply non-local. That means the behavior of one particle can depend on the configuration of distant particles in a way that does not fit ordinary classical intuition. So pilot wave theory restores some definiteness, but it does not restore the old comfortable universe of simple local clockwork. It shows, once again, that any interpretation able to match quantum experiments must accept something strange. There seems to be no doorway back to a fully ordinary picture. There are other interpretations too. Some focus on information. Some treat the wave function as a reflection of knowledge or belief about possible experiences. Some modify quantum mechanics itself by introducing objective collapse, where wave functions physically collapse under certain conditions. Some take the role of observers, systems, or relations in new directions. These approaches differ in what they think the wave function is, what measurement means, and whether quantum probabilities describe reality itself or our relationship to it. The list can become surprisingly crowded, like a philosophical waiting room where everyone has brought equations. What makes this debate so fascinating is that many interpretations preserve the same tested predictions. In ordinary laboratory situations, Copenhagen, many worlds, pilot wave, theory and other interpretations often agree about what experimental result should be expected. They disagree about what the result means. This is why interpretations can survive side by side for so long. If two views give the same measurable predictions, experiment cannot easily choose between them. Physics then becomes partly a question of mathematical clarity, conceptual elegance, philosophical cost, and how naturally each view handles known phenomena. That does not mean the debate is pointless. Interpretations shape how physicists think about measurement, information, probability, and reality. They can inspire new questions and sometimes suggest new experiments. They also matter because quantum physics is not only a calculation machine, it is one of humanity's deepest descriptions of nature. Wanting to understand what it says is not a decorative extra, it is part of the scientific instinct. The difficulty is that the theory works so well while resisting one simple human-friendly story. So the meaning of quantum physics is still debated because the predictions are clearer than the picture. The mathematics can tell scientists what will happen with astonishing precision, but the question of what exists before measurement, what the wave function really represents, and why definite outcomes appear remains open to interpretation. Copenhagen emphasizes practical outcomes. Many worlds keeps the wave function evolving into branching realities. Pilot wave theory gives particles definite positions guided by a real wave. Each story keeps something and pays a price somewhere else. Perhaps that is part of quantum physics' lasting power. It does not merely give strange facts about small things, it forces a deeper humility about what explanation means. The same experiments can be described by different stories, all trying to make sense of a world that refuses to become fully classical again. The debate remains difficult because quantum physics is not vague, it is precise. The mystery survives not because the theory fails, but because it succeeds while leaving reality harder to picture than anyone expected. After the interpretations debate, quantum physics arrives at a calm but unusual place. The theory is not fragile. It is not a half-formed guess waiting nervously in the corner. It is one of the most successful scientific frameworks ever created. It has survived experiment after experiment, across scales from atoms to materials to particle physics. It has helped build technologies used every day. It has explained details of light, matter, chemistry, magnetism, and information with extraordinary precision. And yet, at the deepest level, the story is still not finished. That combination can feel surprising. Usually if a theory works incredibly well, it is tempting to assume that it must also provide a complete picture of what reality is. Quantum physics resists that temptation. It works with almost unreasonable accuracy, but it still leaves open questions about measurement, interpretation, gravity, and the full structure of reality. This is not a failure, it is the frontier. Science does not end when a theory becomes powerful. Sometimes that power simply reveals the next layer of mystery more clearly. Quantum physics has been confirmed across countless experiments and technologies. Atomic spectra match the idea that electrons occupy allowed energy levels. The photoelectric effect supports the photon description of light. Electron diffraction shows that matter has wave-like behavior. Bell tests support quantum predictions about entanglement. Precision measurements in quantum electrodynamics match experiment to astonishing detail. Lasers, semiconductors, atomic clocks, magnetic resonance imaging, and many modern sensors all depend on quantum rules working reliably enough to become engineering tools. That last point is worth sitting with for a moment. A theory can sound strange in words, but if it lets engineers build devices that work again and again, it is doing something deeply right. Quantum physics is not merely an idea floating above reality. It has been tested in laboratories, embedded in technology, and woven into modern civilization. Every time a transistor switches, a laser emits coherent light, an atomic clock keeps time, or a spectroscope reads the chemistry of a distant star, quantum physics is not just being discussed, it is being used. But there's another great theory of modern physics, general relativity. General relativity describes gravity not as an ordinary force pulling through space, but as the curvature of space-time caused by mass and energy. It explains planetary orbits, gravitational lensing, black holes, the expansion of the universe, and the way time itself is affected by gravity. Like quantum physics, it has passed demanding experimental tests. It is elegant, powerful, and essential for understanding the large-scale universe. Even satellite navigation systems must account for relativistic effects to remain accurate. The difficulty is that quantum mechanics and general relativity do not yet fit together as one complete theory. Quantum physics rules the small world of particles, fields, probabilities, and uncertainty. General relativity rules the large-scale world of space-time, gravity, planets, stars, galaxies, and black holes. Most of the time, this separation works beautifully because the situations are different enough. An atom does not need the full machinery of curved space-time to explain its electron orbitals. A planet does not usually need to be treated as a quantum wave function to calculate its orbit. But there are places where both theories are needed at once. The centre of a black hole is one, the earliest moments of the universe are another. In those extreme situations, gravity is intense, matter is compressed, energies are enormous, and the usual separation between quantum physics and general relativity begins to break down. Physicists need a theory of quantum gravity, a framework that can describe gravity according to quantum principles, or reveal a deeper structure from which both quantum mechanics and spacetime emerge. So far, no final experimentally confirmed theory has been found. There are many serious approaches. String theory suggests that particles may be understood as tiny vibrating strings, and that gravity can fit within a broader quantum framework. Loop quantum gravity explores whether spacetime itself may have a discrete quantum structure. Other ideas look at holography, black hole information, emergent spacetime, causal sets, or new ways to understand quantum fields and geometry. Each approach has insights, challenges, and unresolved questions. The difficulty is not a lack of imagination. It is that nature has not yet provided enough accessible experimental clues to settle the matter. This is why black holes are so important. They are not just cosmic monsters with dramatic public relations. They are places where quantum theory, thermodynamics, gravity, and information seem to meet. Hawking radiation suggests black holes may slowly lose energy. Black hole entropy suggests a deep relationship between information and the area of an E-event horizon. The black hole information problem asks what happens to information about matter that falls into a black hole. These questions are not decorative puzzles. They may be clues to the missing connection between quantum physics and gravity. The measurement problem also remains open at the level of meaning. Quantum theory tells physicists how to calculate probabilities and predict outcomes, but interpretations still debate what the wave function really represents and why a particular result appears when measurement happens. Decoherence explains why large systems look classical and why interference disappears into the environment, but it does not satisfy every question about actuality. The detector clicks. The result is recorded. The mathematics predicts the statistics, yet the deeper story can still be told in more than one way. So quantum physics ends this journey in a place of both confidence and humility. Confidence because the theory works. It has earned that confidence through experiments, technologies, and predictions of extraordinary precision. Humility, because the theory also shows that reality is not obliged to match the pictures human beings first invent. Certainty softens into probability. Matter behaves like waves. Light arrives in packets. Empty space has structure. Particles can be linked across distance. Measurements produce definite outcomes from fields of possibility. The world is lawful, but not always intuitive. That may be the most honest way to understand the strangeness. Quantum physics is not strange because it is vague. It is strange because it is clear in a language the everyday mind did not expect. It does not loosen reality into fantasy. It tightens reality into rules that are more subtle than common sense. Beneath the ordinary surface of tables, lamps, bodies, stars, and quiet rooms, nature keeps patterns that are probabilistic, discrete, relational, and precise. And still, the story is unfinished. Somewhere beyond today's theories may be a deeper framework that explains measurement more fully, unites quantum mechanics with gravity, and reveals why reality has this particular quantum structure at all. Or perhaps the deeper lesson will be that some of the questions need to be asked in a new way. For now, quantum physics remains both a triumph and an opening. It explains an astonishing amount of the universe, while leaving the universe just strange enough to keep calling science forward.